Welcome. Welcome to the human side of virtual reality. My name is Jason Gerald. I'm co-founder and principal consultant at NextGen Interactions. And together with Joe Lavoila of the University of Central Florida and Richard Marks of Sony, seated down here, we have over 60 years of experience creating VR systems and applications. So we're going to attempt to condense that down into 3 hours of VR goodness. We'll see what we can do. Okay, we're going to start with a basic overview of human-centered design as it relates specifically to virtual reality. That will allow us to form a basis for more advanced interactions that we'll be talking about, and a whole lot of examples of implementing those interaction design concepts within VR. And Joe's going to discuss some specific examples of how to select and manipulate objects within VR, and then Richard will discuss some specific technologies and avatar interactions. Then hopefully we'll have some time left to conclude and have a discussion with some questions. Okay, so for my part of the talk, much what I'll be covering comes from my book, the VR book, Human-Centered Design for Virtual Reality, thevrbook.net, and sort of, some of the things I've learned, but also from others at great conferences like SIGGRAPH. Heavily references a lot of work, including Joe's book he'll be mentioning, and not necessarily a leisure Sunday afternoon read, but dramatically simplified, right? You don't have to be an engineer to understand this book. I wanted it to be accessible to really anyone. So there's, in the book, there's no code, no equations, very similar to this course, where the focus is on the design from a human-centered approach instead of a technical approach. Okay, first thing I want to talk about, I've seen some crazy technology, some crazy VR over the years. However, for me, there's really one specific type of technology that is the most exciting and really sticks out, and I'd argue is essential. There's a lot of different ways to do virtual reality. The most recent, trend has been head-mounted displays. There's other ways to do it, but really, without this technology I'm thinking about, I'd argue that virtual reality is not possible no matter what type of crazy tech you're using. And unfortunately, not a lot of people, they're aware of it, but they're really only vaguely aware about it, and they don't really think about the technology much, even though it's been around for quite a while, right? It's actually been around thousands of years or even longer. And that, of course, is this thing called the human brain. Now, what's amazing about this brain is it's a massive parallel machine, and it's not the brain in it, it's what's in the brain, right? We have these things called neurons inside of our brains that are really the basic unit, and the communication between those neurons is what's really amazing. And so, on average, there's thousands of these connections called synapses from neurons to other neurons. And there's 1 billion of these synapses, connections, for each cubic millimeter of brain matter, right? 1 billion is a pretty big number. But what's even more amazing is 150,000 kilometers of nerve fibers in a single brain, right? That's a big number. We could literally circle the Earth multiple times if you stretched out those nerve fibers in your brain. It's just mind-boggling to think about. And it's also massively parallel. So these neurons, on average, can reach any other neuron by traveling through only 6 other neurons. That's 6 degrees of separation. So when it comes, a lot of people try to compare computers to the brain, and to me that just doesn't make sense. They're just a completely different type of thing. Computers are good at some things. The human brain is good at some things, and it's really like comparing apples to oranges. They're just entirely different. It's also kind of difficult to think about the brain as something technical, and how do we perceive things out in the world, because we don't perceive with our hands. We don't perceive with our ears or our hands, right? We perceive with our brains. That's just sensory stimuli coming into our brains. And as a result, our perception of the world, of the real world, or in our case with virtual reality, the virtual worlds, it's not really the truth that's out there in the world. we're not perceiving those objects out there in the world directly, where instead we have an interpretation of what that physical reality is. So as I'm looking out in the audience, it's not like, these different objects, chairs, people and such are poking me in the back of the eyeball on my retina, right? It's a very indirect way of, the photons bouncing around. You guys all know about that being at SIGGRAPH. And so our sense of reality can be quite distorted. It's different, of course, for different people, or in this case, different for cats, and also under different situations, right? Different circumstances. Tomorrow I might perceive something slightly different than I do today. So it's really important to understand who your user is, who your targeted user is, and if you try to sort of make everyone happy, you're likely to not make anyone happy. Another example of that, a non-visual thing, is a song, right? Obviously, music can be very emotional, and so I might get emotional if some song means something to me for whatever reason in high school, but if you've never heard the song, who cares? It might not even, you might not even notice that song. So really our interactions within the real and these different virtual worlds starts with perception, of course. And virtual reality, I'm sure you guys are well aware of this that have been doing VR, is it's much more than just graphics. Graphics is obviously important, but it's not the only thing. And so, of course, we definitely kind of gravitate towards that, especially being here at a SIGGRAPH conference. Myself, I come from a background in computer graphics, but there's so much more, right? There's obviously audio, we all know is important, but typically it's kind of thrown on as an afterthought after we've done all the visual elements. But if we can start designing from the beginning of that, that can make a huge difference as far as the emotional impact and such. And the lack of physical touch is really difficult within virtual reality. We can sort of have these, very simple, buzzers and such on our controllers, but it certainly is pretty difficult to replicate something that's as if it was, a real physical object in the world we're used to interacting with. And then there's proprioception that we really take for granted. We don't think about too much. That is the sense of where our body's parts are located in space. So for example, I can close my eyes, and even though who knows where my hand is, well, I know where my hand is because I have proprioception, I can touch my nose, right? It's not a problem. And we sort of take that for granted until something goes wrong, and then you fall over and you definitely notice. And so that's a challenge. It's very related. Some people, the vestibular system, they kind of have that a subcategory of proprioception, depending who you ask. But that's that sense of balance and physical motion in the world. And we'll be talking a little bit about that, of how that sense of balance, if it doesn't match your visuals, then that can cause you to get sick and have a really bad, horrible experience. So it's really important to think about these things that we normally take for granted. Of course, smell and taste, those are important. Certainly people are working on those, but a much messier problem of dealing with chemicals and such. And then also bringing the senses together in a coherent manner. That's really important to have sort of these compliances of, what am I seeing? Does that match what I'm feeling? And if that's a little bit off, it can, be just, a minor thing of feeling a little bit off, or it can lead to that sickness if, the visuals are delayed in a different way than what I'm physically feeling. And so definitely challenges there, and we talk a lot about multimodal sort of output, things coming into the human, but what about also multimodal input from the human to the system? That's where it starts getting really interesting, gesture recognition combined with voice recognition, for example. That becomes really difficult, partly because, you're putting these complex components together and things can go wrong, but that's where virtual reality starts getting really exciting. Now, because we can't do some things well within virtual reality, like the sense of touch, we can in some cases, but it's pretty difficult to do. What we can do is use something this is an example of sensory substitution, right? It's something that, doing something more that requires some creativity beyond how we think about interacting in the real world. And so just like it sounds, we replace one sensory modality with another. So some examples, I reach out and touch something because I'm not physically touching it, that I can simply provide a highlight, for example, here in Cloudhead Games, the gallery, right? That hand is highlighted only when it intersects the object. Or maybe the controller vibrates, for example, or you can add an audio cue when you have those intersections. So lots of sort of perceptual tricks we can do, but we have to be careful of those perceptual tricks, because a lot of times what we think will work within virtual reality ends up being a terrible idea. So lots and lots of iteration and experimentation, but that's what makes virtual reality really exciting. Now, having a background, however, in sort of a lot of, what excites me about virtual reality is bringing so many different fields together, right? It keeps it interesting, but especially perceptual psychology. Some of those concepts that were important before, now suddenly they become really important for virtual reality. And so I think studying things like psychology, sociology, sort of those softer sciences has never been so important as it is now for virtual reality. And so here's some kind of examples of things to think about. We certainly don't have time to go into all these things. We could spend an entire semester on this, but or if you're a grad student, you could spend just one of these topics alone. You could spend 5 years studying it. So the point isn't to go into each one of these topics, but the point that there's a lot to consider when designing for humans. And there's plenty more, right? These are just some examples. But we will touch upon a few of these points throughout the course today. Now, sort of how does that all come together? Well, this is Goldstein's iterative perception action process. So, how do we perceive the world, then how do we get feedback, and then we take action upon the world? It's this continual loop. And virtual reality really is all about this constant feedback loop of what you see and actions affecting the world and such. And so it's basically a model of how distal stimuli out in the world reaches our receptors and how we process it and act upon that. And so then we start paying attention to it, and as we pay attention to it, those sort of that energy reaches our sensory receptors and then is transduced into other signals that the brain processes. And then, of course, we start to perceive those distal stimuli and start recognizing objects and such at a higher level. And then we can act upon the world, modifying those distal stimuli, and the process continues. And this can also be simplified, sort of maybe an easier way to think about it is really it's just the stimulus to the physiology, to the perception, then back to the stimulus. But it's actually more than that. It's much more complicated than that. We're more than, as human beings, we're more than a stimulus-responsive, iterative cycle machine sort of thing. We're a function of the environment, of our, previous experiences, this top-down processing here. I mentioned earlier about, everyone's different, right? A song may affect me differently than you, or, my beliefs very much, affect how I perceive the world. And so what's cool about that is we have a little bit more control, and that allows us to tweak that cycle a little bit and the world in a more conscious manner. Now, where it gets really interesting, of course, is when we put a virtual reality system between that action and that distal stimuli, and the human output becomes the VR input, and the VR output behaves as that distal stimuli. And thus we're hijacking that human perception action system and replacing the real world distal stimuli with these artificially created cues that then our minds, our brains sort of interpret that as a form of reality. And then the system, of course, senses whatever tracking or button presses, whatever we're doing, those actions in order to update those distal stimuli. And as a result, the user experience, VR is all about the experience, he sort of experiences presence in this artificial world as if it was real. And this is all that, sort of academic sounding here, but VR, as you all know, is a very visceral experience. You just have to try it for yourself. It's experiential in its purest form. So that naturally leads into action, right? We perceive something, then we take that action. They're obviously closely intertwined. In fact, some researchers, they believe that purpose, right? That's the purpose of perception, is not to create just a representation of the world, just to be, experience it, but they're to guide actions so that we can influence our perceptions and interact and learn and be able to survive another day, or in today's term, maybe it's survive long enough to play another game. And what's really interesting is how much perception and action affect each other, and thinking about what action we're going to take. For example, distance judgments are further. So if you put a heavy backpack on me and you say I have to carry that backpack up a hill, and I know I'm going to actually have to do that versus just thinking about it, then I'm going to perceive, this has been shown, that you perceive distances to be further. Or successful baseball batters, for example, they actually perceive the baseball the baseball to be larger than those that aren't very good at it, or field goal kickers for American football. They perceive the goal posts to be further apart if they're good. It's pretty amazing how these all relate to each other. And of course, you guys are all aware here, sort of some obvious actions, as simple as pressing a button or directional gazes if we don't have buttons, making gestures, or even just walking around the world, right? That's if you have an HTC Vive or one of the crazy systems you've seen out on the floor with the wide area tracking. That is a form of action that then affects what we see. And things like voice interfaces and all kinds of fun stuff we can do. So I looked at about 100 or so interaction techniques and looked at sort of what are the common themes here and organized them into sort of these meta patterns. And very different than software design patterns. A lot of you are kind of probably familiar here. These I kind of think about as patterns from the user's point of view instead of the developer's point of view of, how do I interact in the world as a user, because we're thinking from the human-centered approach instead of the engineering approach. And then I organize these 5 patterns here into 16 sort of more specific patterns, and then what I call interaction techniques are specific example implementations of those things. And so we're going to be talking about, giving some of those examples, all 3 of us today. Joe's specifically going to be talking about selection and manipulation, and Richard's going to talk about some more sort of advanced compound patterns and such. I don't know if they call them that, but that's kind of how I think about them. So maybe slightly different words, but really the similar concepts there. So that's where it gets cool when we'll start showing some examples and such. Okay, so let's now talk about this ugly thing called discomfort or sickness, VR sickness. And it's not just about motion sickness. That's definitely a big one, but not the only one. So there's some others listed here, right? Eye strain. There's big challenges some people here, I'm sure at SIGGRAPH, are working on of sensory conflicts of, what my eye feels like it's seeing, what's in focus doesn't necessarily match how my eyes are converged on something close. And so we're not going to get into the details there, but there's sort of a lot of things to think about here. I'll be talking a little bit about motion sickness and physical fatigue, but you can see certainly there's others certainly to think about. Mostly physical fatigue. I highlighted that because that's really important when it comes to interaction with your objects, right? If you have your interface up here all the time, then you're constantly doing this, you're going to last about 30 seconds and your arms are going to get tired. It's a really common problem, but it's actually pretty easy to solve, right? You put your interface down here. And so, there's all trade-offs for all these things, but once a while up here is okay, but sometimes you do want the interface up there. It just kind of depends what you're trying to do and what your hardware is capable of and what your design constraints are and such. So we'll be talking a little bit about reference frames of where we place those objects. Do they always travel with my body? Or are they located sort of in the virtual world? Or are they located in the physical world? Lots to think about there from a human-centered design approach. Okay, so instead of, there's, as I mentioned, a whole lot to think about. Actually, I'll skip ahead to this slide. These are some of the things to think about. When you talk to a lot of VR experts, it's really an expert working on a specific problem because he's looking to, sell his product, or that's his area of research. And you hear all the time, we solved motion sickness, or we solved VR sickness. But really, they're working on a small subset of that, right? There's a huge number of variables that need to be solved here in order to create really good systems that don't have those adverse effects that are, very comfortable. And so these are ones that we know about, some being proven, some more hypothesized, but there's probably a lot more that we don't know about or we haven't thought about. Now, I divided them into sort of system factors, individual factors, and application factors. System factors, some of the high-end VR is getting really good at solving those things, right? Low latency, the systems are calibrated really well, a lot of those things. And so as VR creators, that's great for us because we don't have to worry about those things so much. We definitely need to be aware of them so that we know, when we're getting a lot of latency and such because we're not doing our job of optimizing our software. But, a few years ago, a lot of those, like latency, were definitely not solved. Now, individual factors That's the point of people are so different. Some people are very sensitive to latency, for example. And so we really need to understand our target audience and how they think as well. So for example, our expectations of how to move through the environment. If I have a virtual motion and I move in this direction, maybe it's not so bad for most people. However, if the person's expecting to move this way and they move this way, it's suddenly, they're not expecting that, and that can actually very much be a factor in sickness. So one example of those sort of mental models, and lots of other things as well. And then, of course, application factors. Those are especially important for navigation schemes. So how do I, if you're doing some form of virtual navigation, how do I travel through the world? And so that's where it gets fun, where we get to be creative and, you know, how do we do something that different than we would in the real world. But if they're not done well, then it can make you sick very quickly. Okay, so we'll talk about some of these challenges throughout the talk, and I know Richard and Joe have a lot to say about those things as well. So that's a little bit complicated, but let's jump back here to say the basics, because you know we don't have time to go into all those details. But at a very high level, is VR sickness. One of the biggest problems is motion sickness. It varies very much from person to person, and as users, when we go in, don't try to tough it out. If you start feeling it even slightly, then we highly recommend to take yourself out, take a break, and come back later. Be well hydrated, don't be hungry. Hangovers are generally a very bad thing to do, to have while doing VR. If we're given demos out on the floor, then remind them not to tough it out. Be very observant of watching them, right? If you can start seeing sweat come off their head versus talking to the guy next to you, you really should be paying attention to them. Or if they're about to fall over, for example, then be careful of that. And non-motion sickness sort of issues, right? Wipe down the equipment periodically, right? You rarely see that at exhibits, and it's a little bit scary. As creators, focus on making those interactions comfortable. And so those initial signs of discomfort, maybe for you it's a little bit, but maybe you're largely immune to it because you've adapted. So you really need to test with different users and such and really try to pay attention to that. And then provide cues. Like I was saying, if you expect to move in one direction and you move in the other, you can provide kind of clues to your users of which way to move, for example. And then, of course, the big one, maybe this should be at the top, is minimizing those visual accelerations. So when you put someone on a crazy roller coaster ride, they're probably going to be sick. You really need to kind of respect the user and not, tumble them throughout the world. And then, of course, the one universal truth is that high frame rate, low latency. That is one thing that is common across all different types of VR experiences. Okay, so here's a few theories. I thought we'd just talk about a couple of these here. Specifically the sensory conflict theory, which is kind of the most accepted theory of motion sickness, and then the rest frame hypothesis, which I have some examples I'll be showing of that. Okay, so sensory conflict, as I mentioned, is sort of the most widely accepted explanation of motion sickness, and that's basically when the environment's altered in a way that doesn't match up with our information across sensory modalities, right? Our vestibular sense doesn't match our visual sense, for example. That's really the big problem. Other types of sensory modalities not matching up can be a bit of a problem, but not as much as the visual vestibular conflict. So that is, your eyes are seeing movement, but your inner ear doesn't feel that movement. And so that can be a big challenge with locomotion, what I call a viewpoint control pattern. So there's different examples of how to get past that. Instead of just pushing a joystick to move forward, for example, that can be nauseating for a lot of people. So, physical walking is generally a much better thing to do, but there's trade-offs to all of these. Real walking, for example, is good for short distances, but what if you want to go further than the tracked space? You don't necessarily want to do that one-to-one tracking. I walk 5 feet this way, then in the virtual world I move 5 feet. And so you could do things like treadmill walking, you can do walking in place, you can do something called redirected walking. Redirected walking is very interesting. That's when you think you're walking in a straight line, but the system is just slightly rotating the world as you're walking forward, and you self-compensate for that, and you end up walking in a circle when you didn't realize you walked in a circle. Take off the headset, you feel like you walked 50 feet, and maybe you just walked in a large, a 20-foot diameter circle. So it can be very effective, but we do need to be careful there because, even if you don't perceive it, it doesn't quite match up your visual vestibular sense. So there's trade-offs to all of these, really depending what you're trying to do. Another form of moving through the world is teleportation. It's actually been around for quite a while. Since 1997 is when Bowman and Hodges studied it. And what they found is, yes, it reduces sickness for sure, but it can be quite disorienting. And so, if I'm transported to the back of the room, I sort of have this, it can cause a break in presence of, whoa, what just happened? Where am I? Which direction am I facing? And so there's ways to play with that by providing cues, again, to set the user's expectation of which way they will be oriented once they're faced in that direction. So like all of these are trade-offs. So another example is you walk into this portal here and you are transported in another part of the scene. Another one is a dynamic field of view presented about, I think, almost a year and a half ago now. Fernandez and Feiner out of Columbia University, they kind of had the realization, in hindsight, it's really obvious that field of view, we're very sensitive in the periphery to that motion that can cause sickness that doesn't match our vestibular cues. So why not, when we're moving, just decrease the field of view, right? Sort of an obvious thing, but people really hadn't thought about this. I know Ubisoft, Eagle Flight, they do this as well. So people are innovating and sometimes coming up with the same solutions. And it turns out most users don't really notice it too badly until, if you point it out, they might start noticing it. But surprisingly, people don't notice it, that fade out of the field of view. Then, of course, when you stop moving, then you can, provide that wider field of view so you have more, better situational awareness. So essentially, this is just less moving pixels because the pixels aren't moving in the periphery and you have less vestibular conflict. And that can help quite a bit. Now, another thing is this rest frame, these rest frames that are essentially stabilized cues in the real world. And so the stabilized cues provide a sense of stability because it's like this lectern here, if this was in the virtual environment, this would be perfectly stable. In fact, I could reach out and touch it and feel like I'm driving a car, right? If the world out here might be moving, but at least this part isn't moving. So this part of the scene if I perceive that as being stable relative to my vestibular system, then that can reduce that visual vestibular conflict. And so sort of an easy way to think about that, I think the easiest way is a cockpit example that I'm in and here's an example of the game E-Valkyrie by CCP Games, right? That the cockpit is perfectly stable. It's only the outside world that moves, and that helps a little bit. Doesn't solve it, motion sickness, but definitely helps. We kind of took those two concepts of the dynamic decreased field of view when you're moving with the rest frames, and we thought about how can we combine those together. We can do these sort of dynamic rest frames. And so this is even better at decreasing sickness than the dynamic field of view because instead of just blanking out pixels, we're providing stabilized pixels. As you move, more stabilized pixels will come into view, and then there's less visual vestibular conflict. So in this case, we also have a cockpit that you can, see fairly well, but it helps with that, similar to E-Valkyrie, the cockpit is stabilized relative to your ear. But once you start moving, we reduce that visual vestibular conflict even further by fading. Basically, you can think of it as fogging up the windows, right? But only as you're moving, which can be a little bit weird, but seems to be pretty effective. And we're actually working with Duke University, formally studying this, and the preliminary results are looking very good. But we hope to have a paper out on that real soon. And so on the left-hand side, I'm simply looking forward. I'm not moving. So you can see out, you can see the whole world, you only see the cockpit. But then when I start moving forward, you can see out the top of the screen and the bottom of the screen are sort of, the window is fogging up basically with that black oily substance. And then in the periphery, in most cases, this is designed for a seated experience. It might be very different for a walk-around type of experience. But in this case, because we're seated, the user, not always, but typically is looking straight ahead. So instead of just doing the fading out the field of view that's attached to your head, actually we do that as well, but we also fade out the sides of the cockpit, because that's likely what's going to be in his periphery. So you see, if you look to the right, more of that is there's less visual motion. We have an example of that here in a few slides. One will, an example showing some other interaction elements as well. Okay, so now we kind of understand the basics of VR sickness, most specifically motion sickness. How do we measure it? Well, here's some ways of doing that. Of course, as any of you know that have been doing VR a while, especially from the academic side, you probably know about the Kennedy Simulator Sickness Questionnaire. It's sort of the standard, but there's other ways of doing it as well, right? You can provide questions within the applications. How are you feeling? Might break presence, but if you're doing a study, maybe you're not going for presence. Or physiological measures. That's sort of a tough subject there. There's certainly not a wide open for research to do your PhD in, for example. Or just observing users. We talked a little bit about watching people as they're doing demos. Let's briefly go through the Kennedy. We don't need to go into details here. Basically, users rate their systems after they go through a VR experience, and then we weight those and add them together to provide 3 scores: nausea, disorientation, and oculomotor. Again, we won't go into detail there, but it sort of is the standard. But there's problems. In fact, with all of these measures, there's problems. So this isn't unique to the Kennedy Simulator Sickness Questionnaire. So you remember that slide where I kind of divided those factors into system, individual, and design factors? Well, it turns out the Kennedy SSQ, the systems they were using were not like what most people are using today for virtual reality, which is head-mounted displays. They were using projector-based systems largely, such as flight simulators and such. So it was designed for a completely different type of system, right? So is it a good fit? I don't know. It was validated for very different types of systems. And then the individual. This was mostly fighter pilots that wouldn't admit to being sick because they didn't want to be grounded. Right? So they're probably going to fill out the question very differently than we are. So maybe it's oversensitive, for example. We don't know. Maybe we need sort of a new type of questionnaire that can be validated with today's type of users. And then, of course, what about the design aspect? Well, these were flight simulators. Some experiences we do today are very similar to flight simulators, but a lot of them are not. So is it appropriate? I don't know. There's a large variance. A lot of times we need a large number of participants, which can be a little bit frustrating. That takes time to run participants through these studies. And it's very, of course, subjective and biased. So it'd be nice to have sort of an objective measure. Now, a lot of these sort of other solutions, there's no perfect answer here. Typically, when it comes to virtual reality, there's almost never a perfect answer. But some of the other ways of measuring sickness also have similar or challenges in different ways. So the point here is think about what you're trying to do and choose the right tool instead of automatically just going with the Kennedy SSQ just because everyone else has done it and it's been done that way in the past. Okay, there's also not a acceptable score. Again, other measures also have that problem. So what we've been experimenting with our work at Duke University is simply replicating what Fernandez and Feiner did at Columbia University of actually asking them within the app. And so we go through different waypoints and then we say, okay, how are you feeling on a scale of 0 to 10? And it's definitely a break in presence. So if you're, don't want to do this for a product you're shipping, but if you're studying that sickness in order to reduce it, then you can get some great data and a whole lot more data than you can get from the SSQ, because you can ask them, every 30 seconds, and you're actually getting it in the moment instead of, oh, do you remember 10 minutes ago, how were you feeling? Or how do you feel now that doesn't necessarily relate to a specific stimulus within the environment. Here you can put this up anytime. Physiological measures, I mentioned that briefly. There's people are definitely looking at that, but that's challenging because those physiological measures can be so noisy. So that's definitely a wide area of open research. Some examples of that: postural stability. That's very interesting. So there's sort of a hypothesis out there. I haven't seen solid evidence to back this up, but the hypothesis is that you start moving a little bit when you start feeling sick, right? Because your body is trying to compensate and balance itself so it doesn't fall over. And sort of the claim is that, sort of the controversial claim that I haven't seen evidence for, is that you might be able to actually know when someone's going to get sick before they even realize they're getting sick. Like, obviously that would be super valuable. Or heart rate. Well, what does that mean if it goes up or down? It might just be because they're excited. It doesn't necessarily mean because they're not feeling well. But sometimes a change in heart rate at least means something. Or skin conductance, or EEG, that I'm sure people here in the audience know a whole lot more than I do. But all these things can be very noisy, but also useful because they're objective measures instead of sort of this, very biased sort of judgments. Okay, so in conclusion, for making VR experiences comfortable, is that we know a lot about adverse health effects, right? But also, we don't know a lot about adverse health effects, this motion sickness and such. We sort of know the basics, but there's certainly a lot we don't know. And again, that's one reason that makes virtual reality exciting. And so that's one of the things we are studying in order to sort of do, breaking the rules. So for example, I'll be showing a video here soon of doing sort of first-person navigation through the world, which a lot of people say, you're not supposed to do that. And I'm one of the first person to say, well, you're not supposed to do that. Then I go do it, breaking those rules and say, okay, well, if we do that, how can we maybe reduce some of those problems? Maybe we don't solve it for everyone, but for, the audience, our target audience, it might be appropriate. And so to innovate, sometimes you need to go against that norm, even though most of us here understand in general it's not a good idea unless for specific reasons you're doing that. Again, trade-offs for everything. So expect to do lots of experimentation and iteration. You will not succeed the first time when it comes to VR. Well, you might. I mean, if you're just going to go in a world and look around, that's fine. But to really make things interesting, you're probably rarely going to get it right the first time. Okay, so I previously mentioned reference frames, how that can help you, for example, with the physical fatigue we talked about. And so thinking about and understanding these reference frames is really important for human-centered design. Mainly, this is SIGGRAPH, right? You guys, most of you probably know about reference frames from computer graphics, right? We have things like, screen space, object space, world space, if something is to the right, is that in screen space or is that in object space? And so those reference frames, they basically define the axes that determine translation along X, Y, and Z, and rotation along yaw, pitch, and roll, and how objects move relative to each other. For example, is a stimulus attached to the head? Is it attached to the hand? Is it attached to an object that moves in the world, and the thing moves with that object? So this is an example. I mentioned at the beginning of the talk, VR is a very visceral thing. This kind of looks complicated, like what the heck's going on with this interface? But you get into VR, these visual elements here are in different reference frames, but it's not obvious from a 2D image. But once you're in VR, it becomes really obvious what those reference frames are, and something you just sort of have to experience. But once you're in there, you get, this visual object is out in the world, and those arrows move with my body as I travel forward virtually, for example. Or the compass on the ground is the direction, the northern direction on the map. And so let's break those down a little bit. So first we'll talk about the head reference frame. And so the psychological literature refers to that as the cyclopean eye. That's just the midpoint between the eyes that serves as our reference point of what is the head-centric straight ahead, regardless of eye gaze, right? So if I'm looking to the right, this is still the sort of forward direction. It's really, all it is the same it's the HMD reference frame when we're using head-mounted displays. And also what you're seeing on a screen when you're observing, you're not in the head-mounted display, but you're watching someone doing it on a monitor over here. It's really confusing because what you're seeing does not match your visual cues, your head motions that the person in the head-mounted display is using. So this reference frame is, a lot of people are doing this now because we don't have, good hand input on a lot of consumer systems. And so they do gaze-directed selection, right? You look at something, line up a little cursor over something, then push a button. Or you have a timer that if you look at it for more than 2 seconds, it will become selected. So that's a great example of a sort of a pointing gaze selection example, if you're, whether you're firing fireballs from your eyes or whatever it might be. You do need to be careful here of minimizing those visual cues, and especially when porting existing desktop heads-up displays to VR, and boy, that's a whole topic in itself that essentially it doesn't port well. You got to be very careful if you are porting 2D games to virtual reality. Okay, so the torso reference frame, those are visual elements or interface, whatever they are, that move with the body. So whether I'm moving forward virtually by pushing on a joystick, it will move with me, it will always be in front of me. Or if I have a walk around experience, then I can physically walk around and it will always be sort of, in front of me. And the great thing about that is you can use that idea of proprioception, what I mentioned earlier about touching your nose, is once you've learned the interface, you might have a bag, for example, to your side that always travels with you. And now I don't even have to, after I've gotten accustomed to that, I might not even have to look at it. I just reach down, pull a button, and pull it up. There's the item that I wanted. Or maybe I might have a toolkit around me that I may not be, if there's a lot of tools, I may not be able to necessarily do it without looking, but if it is relative to the body with that sense of proprioception, I don't have to think about it as much. It's much more natural when I'm feeling it relative to my body instead of only having the visual channel. So whether it's sort of a utility belt that's surrounding you or a sort of information display, maybe it's data only that you're not really interacting with, it can work pretty well. Now the challenge with that, of course, to do that well is you need to track the torso. Or maybe you're seated in a chair so you can kind of fake it and track the chair. Maybe that's good enough if they're not going to move around on the chair. If it's a seated experience where it's not a swivel chair, then you can estimate it pretty well which way is the forward direction. But if the user moves in some big way, then it can be a challenge. So it works well with steering where you're moving in the direction relative to the torso. There's actually a lot of different trade-offs to think about that. It goes back to what I was saying about expectation. If I expect to move in this way and I move in this way, well, things will be off and you're likely to get sick. But if you're tracking the torso, you know which direction forward is. Or if they're seated in a chair, you can assume which directions forward is. But if I suddenly do this, then push forward on the joystick, then I'm moving this way because it thinks I'm moving in that way. That can be a problem. Then, of course, there's the virtual world reference frame, and that's what any game developers are placing assets in the world. You're very familiar with that. So it's good in terms of thinking about geographic position and direction, north, south, east, west, large-scale navigation. I don't necessarily want to do it from a first-person perspective, and when forming sort of this cognitive map of the world. Unfortunately, they're often not very useful for, not very friendly anyway, for interfaces. Because especially if I have to do a virtual sort of navigation, I have to take my character that I'm controlling, and if the interface is over there, I have to navigate over there. Not just move over there, but I have to rotate appropriately. Because if I'm trying to interact in this way, then my arm's going to start getting sore because, I'm bending my hand at an odd angle. So you have to be a little bit careful of that as far as interfaces go. Now here's an example of sort of a mix of a virtual world reference frame and a virtual world reference frame and a physical world reference frame, where the orientation of the compass is in that virtual world reference frame, but it actually moves with me. So it's sort of in my torso reference frame. So it's this really weird mix. But the idea is that it's very easy when you're doing if you are doing a virtual rotation type of interface where you rotate virtually instead of physically, then it can be very strange. You get lost really easily because I know I turn 90 degrees because I have that sense of physical change in orientation. But when I do it only visually, then suddenly which direction, wow, was I facing north? What happened? That sort of intuitive sense goes away. And so providing a compass, this is one example, the compass sort of down at the feet can really help with that. There's other ways to do compasses. That's just one example. Okay, now the real world reference frame. This is not what a lot of people think about because they say I'm in VR, everything's virtual, but you are still in a physical world even though you're not seeing that physical world. So this lectern is in the physical world. And so now I can line up my visual elements with props out in the world. You don't even need to track this thing. If you know it's not going to move, I can match the visual elements to this, and now I can reach out and touch it and see it. Maybe it has a different texture, slightly different, but it matches what I'm seeing, and wow, that takes presence to an entirely new level. Sort of, definitely not a high-tech technology, but sometimes the simplest things can be super effective. Or if you want to track props in the world, right? So if I wanted to track this thing here, then I could reach out and move it. Or hand controllers, for example. Any of you use the HTC Vive, even when you don't have them in your hand, you can still see the thing on the floor. So that's in that sort of real-world reference frame. And also the rest frames I talked about, the cockpit example, that's sort of in the real-world reference frame, right? If I move forward, I get closer to the windshield. It's as if, there was a physical real-world cockpit around me. And so that can really result in that dramatic reduction of motion sickness. Another example of that is a non-motion sickness solution. Any of you use the HTC Vive, you have the chaperone system when you get close to a wall, right? You don't want to punch your hand into the wall, so this can help with safety, so you're not damaging the equipment or yourself. This is another example here as you get close. That sort of faded in grid pattern, hexagon grid pattern there means that there's a wall there and danger, well, slow down. It sort of just fades in as you get close. Okay, so reference frames, the point here is, think about those and choose wisely of what you put your interfaces in, right? If they're hard to reach or they're always up here, then your users are probably going to get tired pretty quickly. You see that actually, it seems like such an obvious thing, but you see demos all the time of, the interface being up here, and it's like, you get sore after 30, 45 seconds. Okay, so now I want to get into making interfaces intuitive. And so we've been playing a whole lot with this of sort of teaching interfaces, sort of training the user of how to use the system or to build something in the environment, for example. And so in the very early days, this can actually be pretty effective, kind of a very simple solution. This is kind of what we started off with when we were trying to teach brand new users of what the heck is going on. You simply put the user interface elements, try to match them up with the, with their hand controllers, for example. These are old school Razer Hydra controllers back in the day, some of you I'm sure are familiar with. But just putting those, user interface signifiers, labels on those hands. So you're feeling just like, you see a lot of demos now, you see the controllers that match what you're physically feeling, but then you can add labels to those buttons, right? Sort of an obvious thing to do, but I see a lot of times, I see like the interface like not connected to the hand, so it has the mapping way down here, and it's like, why aren't the mappings just, attached to the hands? Makes it much more intuitive, even though obviously we don't have finger tracking here. It's kind of close enough, and you can kind of feel around where those buttons are. And then, of course, after you get good, you don't need that anymore. So you want one of those buttons is, I think the mappings button there is to turn it off. So, after you know how it works, you can turn it off. So it helps, but we can do better. So we started to explore it gets sort of to the point of, okay, instead of just conveying to them visually what's going on, of kind of providing a clue, how can we really teach them the interfaces so their first time with an entirely new interface, they'll get it without requiring the luxury of going out here on the show floor and having the guy who created the demo, tell you how it works, tell you what's wrong, and to answer your questions and such. When we ship into people's homes, we don't have that luxury. And they're probably not going to take off the headset and read the user manual. And so here's another early example where we started to experiment how to teach these concepts. This was kind of more on teaching, this was basically a 3D brain puzzle where we're trying to teach kids about different parts of the brain and what parts of the brain affects what part of the body and such. But really kind of started leading into our work with tutorials. So I will go ahead and play that.
Make the needle touch the problem brain part for 3 seconds, and if you pick the right part, he'll be healed. Now watch how Fred behaves to see if you can figure out which part to heal. My right hand feels it, but not my left. Now heal the part that's causing the problem with the hypodermic needle.
Okay, so sort of our first attempt at a tutorial, and we found Our friend, you can see our great voice talent there. That's the lead developer voice. We can do a lot better in this, but at least it was providing us kind of ideas where we can go. And so we put this in schools for kids to kind of teach them these concepts. Basically, you know, it's a prototype, getting feedback, what works, what doesn't work, all of that. And we found we still had to be there and tell them what to do. This was not good enough for them just to pick up and understand it. So we continued exploring that, and really what we got is that it's, you know, what are the important concepts here, right? And if you go back to the, you know, Don Norman, you know, human-centered design sort of literature, then he sort of has a lot of those answers, right? He applies to those to the real world, but they apply very much to virtual reality as well. So we want to help convey basically those consistent conceptual models of their expectations and such through teaching those things like affordances and signifiers and feedback, and that's a whole nother talk. But what we found kind of in general is, of course, simplifying the interface, right? Making it as intuitive as possible. Of course, that's challenging when you have more complex things. And so we'll show some more complex things here in a moment. But that's often the most difficult thing, of simplifying something to its core, but not oversimplifying where it's not useful anymore. We also found hierarchical steps to be really important, where those hierarchical steps, sometimes they're linear, sometimes you need to do some things in you know, a consecutive way, sometimes in a concurrent way. Finish all 4 of those until you finish that larger step. You have to finish all 4 sub-steps. In other cases, maybe you don't need to have the audio finish playing, for example. If they finish the other 3 steps, then you can skip the audio. You can, you know, just end the audio. They already did it. You don't have to explain it anymore. And that relates to the completion criteria of what is required for them to continue on to the next step. So essentially, you don't continue until they've taken some action. Related to that is repeated audio. If they haven't gotten to the completion criteria, maybe we repeat the audio in a slightly different way to remind them, right? And a big challenge here is attention of, you know, audio by itself. We found, and talking to others, they found that no one really listens to audio. But when you put other things in, multimodal cues with that audio, then suddenly they'll start listening. Or if you require some action and they can't go on until they've completed what the audio told them, then audio suddenly starts working. And so I have an example of these things, but I also want to mention before I show this example is a lot of these interfaces are really abstract, and they're kind of a break in presence. Like, why the heck is this weird interface element floating in, you know, in front of me when I'm supposed to be out in the world? And so if we can incorporate those abstract interfaces into the story of our games, that's where it gets really fun. Of course, there's no easy answers there, right? But at least it's we get to be creative. So, you know, depending how you look at it, that's a tough problem, but it's also a very fun problem. And so we struggled with that a lot with this sort of fun little side project game we've been working on of, you know, how do we incorporate this really abstract Xbox controller interface into the story of the game? And so I'm going to play a video here. And essentially what you're doing is you're flying a drone, and of course a drone requires an interface. And so you see the interface down there is the Xbox controller. And now we're teaching the interface of what those buttons do. So this is sort of the splash screen. We're not really teaching at this point. We're kind of assuming they know selected gaze-based interaction. So here he's just going to look at the training level and then push play.
Establishing neural link with pilot 727.
So now he's entering the tutorial.
Thank you for choosing Next Gen Games Remote Telepresence System T32.
So there, part of the story is that you're in a remote virtual reality telepresence system. The story of why are you putting this head-mounted display on the head? Well, we actually made that part of the story because you're flying a VR drone.
Welcome, pilot. Sit back, relax, and enjoy your training.
Okay, so that's essentially the cockpit that also acts as a rest frame that I talked about, similar to the Eve Valkyrie, and then a representation, because we know, in this case, we're assuming the user's seated, so we know the forward direction, so we are kind of guessing that that Xbox controller is approximately in that forward direction. I'm not sure if you saw it, but there was an arrow pointing to the button at the bottom, right? And it's
Best
animated to
option is
kind of get their
run
attention.
by holding down the left trigger while pushing the left analog stick. Safety block dropping in 3, 2.
So it starts with a corporate motivational soundtrack,
Remember, electricity hurts.
and it kind of turns into this
Re-energizing thrust.
this intense
Unfortunately, the
experience,
T32
because that's what the
system
game
has
evolves
limited
into.
energy that only allows short bursts of thrust. Do not worry though. Few trainees have died, like followed instructions.
So we're just basically teaching them how to move through the world. That's all we're doing.
Congratulations, you survived. Your health will regenerate soon. To celebrate, please spin in a celebratory circle by pressing the
So
right
there's the arrow
analog
again.
stick, left or right.
And we intentionally did not listen here to convey that repeat audio. If they didn't hear it that first time, we'll now repeat it.
You will spin in a celebratory circle. Yay, that was fun. Did you notice the
Now listen very carefully. I talked about that dynamic rest frames. We're doing that here. I don't know if you noticed it or not, but we actually point that out to the user of why the heck is this weird thing happening in my periphery. We made it part of the story. It's part of the drone technology to reduce sickness, because you're in reduced motion sickness in this virtual reality telepresence system. And so now it's going to explain that.
oily anti-vestibular coating that appears on the cockpit sides? All T32 telepresence systems
And so when he's
include
moving,
this
there's
feature
less visual
to help
vestibular
fight
contact.
nausea often associated with virtual reality. It appears when motion is detected and recedes quickly. You can turn off this comforting feature by pressing
And now we're
the
touching the
Options
menu
button.
system. Again, it's part of the drone system.
The Options menu provides more control of your drone, such as modifying settings, where comfort mode can be turned off. Select the Resume option to continue your training. Settings.
So, you know, like in a typical game, just being able to control those things. Some people are immune to motion sickness and they don't like that dynamic rest frame, so we allow them
You've
to
done
turn it
well,
off.
thus far. You will be rewarded for your submissiveness.
Okay, so that's one example that we found works pretty well. When we put people, you know, we seat them at a conference or wherever we're demoing, we don't have to sit and explain that interface. We, you know, just put them in there and say, let's see how you do, and then we observe them and see what they were missing and what we messed up, but not interfering with how they'd experience it in someone's home. Okay, so another example, this is one of the most exciting projects I've been working on with HTC Sixth Sense and Digital Art Forms is Make VR, which is essentially a 3D modeling package actually, you know, connected to the ASUS CAD engine. And how many here are CAD people? I would think a lot more. So those of you that might be a reason why a lot of you aren't CAD people, because the learning curve is pretty intense to learn, you know, AutoCAD or Maya 3D Studio, whatever thing it might be. There's a learning curve there. And that's the huge challenge here. VR by itself is not intuitive, even though, you know, we say it's intuitive. It's only intuitive if you design it well. And so teaching sort of complex modeling, Boolean operations and such just within a few minutes was a huge challenge and a major concern for this. But based off of, you know, exploring with those other sort of tutorial things we were doing, I think we got, you know, had been learning some things, and this has worked out pretty well. So we're teaching CAD and sort of the basic things in 10 minutes, and more recently we've been teaching more complex operations as we start incorporating them into the world. And without this tutorial, I mean, I was a guy working on this, right? And I didn't know how things work. It was confusing for me. So this tutorial just made all the difference. I don't think this would have succeeded at all without that. By the way, who here has tried Make VR? A few of you? Okay, well, this is what it's about. This is sort of tutorial number 3. Tutorial number 1 is really simple. It's like poke the object with your stick and pick it up, right? But some people don't get that, right? They think you have to point. You just don't know. And so even the basic things. But here we're teaching a Boolean. I think we're doing additions and subtractions and changing material and such on the objects. How do we change the textures on an object, right? So I'll go ahead and play it.
Select the color and texture icon.
Okay.
Pick a texture icon on the fold-out panel.
All right, so I gotta hold it out here.
Graph the unattached antenna.
By the way, this is provided by Fishbowl, which it seems I lost my icon somehow. But Fishbowl, basically, you send this out to their users, and they have different options. Here, we're getting an actual video of what the user's doing, and if you're lucky, you'll get a user that talks out loud. That is so valuable. It kind of gets what he's thinking as he's going through the interface, and you quickly see what's wrong with your interface if he becomes confused.
Press the blue Go button.
Okay, it does show texture. Huh?
The material of the entire selected antenna object changes.
Okay.
However, you often only want to change the material on part of an object.
Wonder if that works.
To do so, select the Face Only checkbox in the Color and Texture Properties area.
Hard to miss with those big obnoxious arrows. Here, the story
Grab
isn't
the
as
stem of the
important, right?
antenna
Because
that
it's
is
sort of a
attached to the
technical thing.
MechBot.
So we can kind of have these arrows, these abstract interfaces,
Notice
because
only
we're just
the graph
teaching that
part of the
interface.
MechBot glows red. Press the blue Go button.
Okay, so you guys get the general idea. Okay, so in summary, for intuiting these interactions is that, in hindsight, it seems kind of obvious what to do, but is often not. Virtual reality is not intuitive by default. It's really a result of, being creative, of design thinking, of a whole lot of experimentation, of course, user feedback, and massive, massive iteration, more so than regular real-world design. Okay, so with that, I just want to close. If you're interested in these sorts of topics, this is what my book's about. And so you can check, actually after the bookstore, Joe's selling his book outside as well. His is an amazing book. I heavily reference early version of his book. His book's more recent, but both of these books, check them out. Take a look, see if it's something that's interesting to you. 600 pages of VR goodness here, lots of theory and application, but also, applicable guidelines, over 600 guidelines here, and a whole lot of references if you want to go back and look at the original papers and such. Okay, with that, we'll have Joe come up and talk about selection and manipulation.
Gotta be kidding. Okay. Why don't everybody stand up real quick and stretch? Because we didn't plan any breaks in this course. So just stand up, stretch out a little bit. Okay, you can sit now. Okay, so as Jason mentioned, my name is Joe Laviola, and I run the Interactive Systems and User Experience Lab at the University of Central Florida. And what I'm going to talk about in this part of the course is selection and manipulation. And it turns out that selection and manipulation is a pretty critical component of interaction in VR, because a lot of the times, you want to manipulate objects. But before I start, of course, I have to give the shameless plug. This is actually the second edition to this book, which was first published in 2004, and it's been pretty amazing doing the second edition to see the amount of things that have changed over the years, over the last 10 to 12 years. So it's been completely revamped, and my co-authors and I spent quite a bit of time, much longer than we expected to, in revising it. But this talk is basically going to be taken right from the selection and manipulation chapter in the book. All right, so we're talking about 3D interaction techniques in general. Choosing the right technique, the right input and output device, you have to think about input device, output device, and then interaction technique. And that really helps make an effective 3D user interface. And the interaction techniques, the methods to accomplish a task in the interface requires, as I said, the hardware component, the software component. And when I say software component, what I'm talking about is control to display mappings and transfer functions. And that's really what an interaction technique is when you're talking about its selection and manipulation or travel and so forth. And we kind of break them up into metaphors and concepts. And they're sort of a set of universal interaction techniques that are out there. And selection and manipulation is probably the most important, but maybe the second most important is how you actually move around in the virtual environment, and that's travel. And then, of course, there's system control, which is actually how you manipulate various aspects of the application. But for the purposes of this discussion, I'm going to spend the next hour talking about selection and manipulation. So when we talk about manipulation, right, as I said, it's fundamental in both the physical and virtual worlds. In the physical world, we do it all the time. There's a lot of different task types when we think about 3D manipulation, and in order to manipulate something, you need to select it. So they kind of go hand in hand. There's different classifications for these manipulation techniques, and sort of the way that we're going to talk about them is basically classifying by metaphor. We're going to talk about grasping, pointing, indirect techniques, bimanual techniques, and hybrid techniques. So when you think about 3D manipulation tasks, what we're really talking about from a broad perspective is the act of physically handling an object with one or two hands. And a narrower definition would then be a spatial rigid object manipulation, okay? And that's that's including shape preserving. And that's not necessarily a requirement. Sometimes you want to change the shape of an object as part of a manipulation, and that certainly is something that you can do. But a lot of times when we're talking about pure selection and manipulation, we're talking about simply translation and rotation without scale. Most of the techniques I'm going to talk about don't do scale, but I do have a couple that do. So the canonical manipulation tasks include selection, okay, which is actually acquiring and identifying an object or subset of objects. There's the positioning, which is changing the object's 3D position. The rotation, which is changing the object's 3D rotation, obviously, or orientation. And then, if necessary, scaling, which is the uniform changing of the size of the object. Now, one of the things that you need to keep in mind is that there are a lot of parameters that you need to deal with when you're talking about selection and manipulation, and people don't really realize how many parameters there are. In terms of both selection and positioning, for example, there's the distance and the direction to the target. There's the target size. There's the density of the objects around the target. There's a number of targets that you wanted to select, right? There's occlusion and how you deal with that, right? Then when you're doing actually manipulation, there's, how far are you manipulating something? Is it fine grain manipulation? Is it coarse grain manipulation? So, it's not just simply the act of selecting something and manipulating it. It's actually, there's a lot of things to think about. There's probably more parameters to think about with selection and manipulation in VR than in doing a computational fluid dynamic simulation. Now, the thing about selection and manipulation too is that they, at least the techniques I'm going to present to you, are very general, and these techniques have been developed over the last 20 years, and they were designed specifically just to try to be as efficient and usable as possible in the most generic sense. But the techniques may not always be applicable to a particular application that you have. So, certain tasks may fail to capture important task properties with these real applications. You have to think about that in mind, that the techniques that you use and you come up with have got to be as close to application specific as you can, because that's going to help you with your intuitiveness of the technique. Okay. Now, a couple of things about manipulation. When we think about manipulation, we think about selection and manipulation in 3D. In VR, we have to talk about the number of control dimensions. How many dimensions are you controlling? Very often it's 6 degrees of freedom, right? 3 position, 3 orientation. Sometimes it can be more. It depends on what it is you're dealing with. There's the integration of control dimensions. Most of the time we want to have all our dimensions integrated together instead of doing them separately. It makes things a little bit easier to do, makes it faster, although sometimes in some situations you may want to have things separate. Then there's also the notion of force versus position control. Typically, position control is preferred for manipulation, where force control is more suitable for controlling rates, velocity, other types of rates of that nature. Then, of course, you have to always think about the input device that you're using when you're looking at 3D manipulation tasks, right? There's very generic devices that can be used. There's very task-specific devices that can be used, and it really depends on what it is that you're trying to do. There's also placement, right? How you actually hold the device, okay? And you can have what's considered a power grip, which is sort of a general all-purpose grip that allows you to do everything. Then you can have precision grips, where maybe you're using just your fingers to do more precise movements. Then sometimes you may have to do clutching, where you actually have to reset your hand on the device and then continue moving. These are all different types of things that you need to think about. Now, as far as classification for 3D manipulation, the main classification that I want to talk about and focus on in the rest of this talk is the isomorphic versus non-isomorphic task sort of classification. And all that really means is, when I say isomorphic, I mean one-to-one mapping, or a more realistic mapping. Non-isomorphic is often considered magical, because what we're doing is we're changing that one-to-one mapping to be one-to-many or many-to-one, or changing the control-to-display ratio such that moving a small amount with the physical device may have the virtual device move quite a bit, or vice versa. And we're going to find that in a lot of the techniques we talk about, there's a non-isomorphic component, which can be very powerful in doing a variety of different tasks. There's also things like task decomposition. You can actually break the tasks down into its individual counterparts, or individual components, and then of course by metaphor. So what we're going to do now is go through a whole bunch of different selection and manipulation tasks and techniques. Okay, we're not going to go into any significant detail in any one of them. We just don't have time, and I'm even excluding some that I talk about, or that we talk about in the book, simply because I wanted to keep the focus more on more immersive VR techniques. So we're going to go pretty quick, and I'm going to do my best to explain each one, and I've got videos that will help demonstrate the techniques. So the first type of metaphor that we think about is the grasping metaphor, and there's sort of two basic ways to think about it. The first one is the simple virtual hand, and this is what everybody thinks about. It's sort of a realistic, direct manipulation metaphor, where you have a virtual representation of your hand in the virtual world, and you use it and you grab objects and you can select and manipulate them. Okay, and that works all well and good as long as the objects are close to where you are. You can actually reach them. A augmentation of that technique is called the go-go interaction technique, which was inspired by Inspector Gadget. And this is the only math I have in the slide, or in the whole talk, but it's really important math if you think about it, because it represents the types of things that you do when you do non-isomorphic behavior. And the go-go interaction technique, basically what it does is it assumes a simple virtual hand. So within a certain distance from my body to some distance d, let's say, okay, I can do simple manipulation. But then when I surpass that, then my hand exponentially goes farther out into the environment to be able to select anything in the room. All right, and it uses an exponential function in order to do that. And you can see the math that describes that, and also the graph there that shows once we hit our threshold d, we start to increase the distance of the hand moving out in space. And it's basically as far as you can go. That represents, you as a person can't go any further, but you can certainly have your virtual cursor, your virtual hand, go as far as it possibly can based on the function that you use. And let's look at a couple of videos that demonstrate the differences here. So here is simple grasping. So in the right-hand corner, lower right-hand corner, that's Puya Kelo, who actually did all these videos for me. Just showing you basic hand, you're not using the hand, we're using the Vibe controller, but it's simply just intersecting the object and then grabbing it and then using that controller to manipulate it. Now you'll notice the difference with the go-go technique. Right? So we can go ahead and select objects way in the distance, right? And he is simply extending his hand outward, but we're using that non-isomorphic function to move the cursor as far as we possibly can. If it's something that's within the user's, sort of boundary of direct manipulation, then they can go ahead and just use a straight, direct, simple grasping technique. This is a very nice combination of combining both an isomorphic approach with a non-isomorphic approach. So you get both a more realistic and also a magical type of property as well. Now, a lot of people, when they think about grasping metaphors, they think about using the actual hand. In the previous examples, what I showed you was using the Vive controller as your virtual representation of the cursor or the 3D mouse or whatever you want to call it. A lot of people want to be able to actually see a representation of their hands and then use those in the virtual world to manipulate objects. And this is what's known as finger-based grasping. And there's a couple of different techniques, and there's a significant challenge with any type of finger-based grasping is that, you have no haptics. So when you're in the virtual world, and you go to grab something, you always have to worry about that your fingers are going to penetrate the virtual object. All right, so there are techniques that we can use and that can actually help stop that and make it a more natural-looking interaction. So with rigid body fingers, which is what they're called, basically with any of these techniques, you need to track the hands and the fingers together. Okay, and you can use a bend sensing glove to do that, or a 3D depth camera, whatever input device you have that's going to be able to give you both the position of your hand and the fingers. And what we basically do is we map the hand and the finger positions to a virtual hand and fingers. Okay, so that as I move my hand in the physical world, I see the virtual representation of my hand in the virtual world. And then what we do is with rigid body fingers, we're actually doing a physics simulation. Okay, and the physics simulation basically uses torsional and linear spring dampers for the fingers, so that when I go ahead and I touch an object, I have spring constants that are in place, so that when I go to grab them, I'm not actually, my fingers actually will slow down a little bit and will be fine-tuned to actually grab the object and not penetrate. But even in that case, all right, sometimes what happens is you get to a point where you're selecting an object, your fingers get stuck onto the object, okay? It's known as a sticky finger problem. So what you often have to do is provide heuristics to support what are known as release functions. And the release functions are basically tell you when you want to release that object. So for example, given some epsilon of the spring force across all 5 fingers would indicate that I am now ready to release an object, for example. And the nice thing about this is you're never going to penetrate them, but penetrate the virtual object, but of course it's rigid, okay? It's a little bit clunky. So what people did was they said, well, let's do a soft body finger approach. And what they did was they said, well, let's do a deformable representation for the virtual finger. So now your fingers, instead of being like rigid objects, they're actually deformable, okay? And if they're deformable, well, that means that they're going to change shape depending on what they interact with. So what soft body fingers does is uses a lattice shape matching algorithm. And what that does basically is it deforms the pads of the fingers to dynamically adapt to the shape of the grasp's objects. All right, now depending on how complicated your objects and how complicated your model, that can get somewhat computationally intensive. But there are ways to speed that up. And when your real fingers initially collide with the virtual objects, the virtual finger pads are going to deform slightly, and you would actually see that in the virtual world. but then there's no real reason, or there's no real indication for when you would stop. So what can happen is the real fingers can actually penetrate the inner space of the virtual objects. And when that happens, what gets done is you add more collision points for the virtual fingers. And those collision points then help to sort of reduce the amount of penetration of the inner space of the object. So it's a dynamic approach to actually being able to ensure that your hand, your virtual hand, doesn't actually physically go into the virtual object that you're trying to select. And this is a sort of a notion between implicit friction compared with rigid body models. Okay. The third one is called God fingers, and this is very strange. Some of the names that we come up with for techniques are very strange, as you're going to see as we move forward. But these are known as God fingers, and they're based on something called the God object. And the God object, why they call it the God object, I really don't know. But the God object basically is a virtual point that adheres to a rigid body physics and physical object and never penetrates a virtual object. So it always remains on the surface, and that's the constraint that is applied to it. And with that constraint, then you can very easily calculate a force direction. Okay, and if you know the force direction, well, then we can do things like compare forces and use force equations to help determine whether or not you're selecting an object and you're grabbing it. So the goal then is to use the God objects for finger grasping and manipulation. And you compute the contact area about the God object, not the God object itself, but surrounding it, all right, as if the surface was flat. And then the contact area basically is fitted to the geometry of the object based on the force direction, okay? And then one of the things you have to worry about are odd deformations, okay, because you figure, you may get some strange deformations depending on the complexity of the objects. You have to deal with angular thresholds between the force directions and the surface normals. And, if you really are interested in this, then you can go to the paper that we refer to that goes into the explicit details. One of the things that a lot of software VR software, Unity and Unreal engines, they have physics support in them already, so it makes it easier to do this type of stuff than actually having to build them from scratch, because it can be pretty challenging to do that. Now there are enhancements to the grasping metaphor. Okay, the 3D bubble cursor, okay, Prism, hook, and intent-driven selection. So we'll talk about how we can enhance the grasping metaphor, make it a little bit easier to do. One of the things that you always notice in VR is you look at the techniques, and somebody can explain the techniques to you, and then you actually go try them, and you find out they're a lot harder than you thought they were. And it simply has to do with the fact that you're dealing with a space that, even though it seems to be familiar, you're not familiar with it, because it's a virtual space where the cues that you have, as Jason talked about, are simulated. And because they're simulated, they're not actually real, and therefore you can get cue mismatches, which cause difficulty. So the 3D bubble cursor is an example of a cursor that tries to help you in selecting objects. And what it does is it's basically a semi-transparent sphere that will dynamically change its shape to encapsulate the nearest virtual object in the scene. Okay, and it's designed for selecting a single object, but what it does is it gives you a little bit of a grace space, if you will. When the sphere is too large and begins to intersect a nearby object, a second semi-transparent sphere basically is created to encapsulate that object, so that this is a way to be moved in approximation to an object instead of actually having to actually intersect it directly, and you use this to help do object selection. So we have a video of the 3D bubble cursor to show you. So we have the bubble cursor, and then as we move towards objects, we can, the other cursor, the inner sphere will show up, and it's a lot easier to select objects. Now you're not actually necessarily touching the objects, but you can be if you're actually going all the way into the sphere and touching an object, but you don't have to do that. Okay, so it's a lot easier to select objects this way. Okay. Now Prism, okay, stands for precise and rapid interaction through scaled manipulation. And I say, well, what does that mean? Well, this is an example, another example of the non-isomorphism that I talked about earlier, okay? We applied a scaled-down motion of the user's virtual hand when the physical hand is moving below a specified speed. So you can imagine you're moving to select an object and your hand is moving at a speed below a certain threshold. When you go below that threshold, what happens? We decrease the control to display gain. All right, so what that means is that if I move a certain amount, my physical hand, the virtual hand, or the virtual cursor, if you will, is going to move even slower. And because it moves slower, I can move my hand this far, right, in physical space, but in virtual space, perhaps my cursor is only moving this much. So that gives me a lot of precision, all right? And this is really good if I have a very dense area of objects that I want to select from, all right? But, of course, the trade-off is that you cause a mismatch between the virtual and the physical hand location, all right? Obviously, if I'm moving this way and then you see the virtual hand is not where I sync up. So what has to be done is an offset recovery mechanism based on the hand speed. So once the hand speed basically reaches a certain threshold, then we go ahead and we actually take the hand and we move it back to the original physical hand location. And that allows the hand to catch up to the physical hand, okay? These manipulations, when it comes to non-isomorphic and control to display mappings, is really important when you're thinking about doing any types of 3D selection and manipulation in virtual reality. Now, hook is a technique for selecting objects that are moving in the environment. And it's certainly a possibility that you could have moving objects in space. And what it does is it basically, the technique observes the relationship between all the moving objects in the environment and the hand to basically develop some tracking heuristics. And those tracking heuristics include computing the distance between the hand and each virtual object, okay? It orders and scores the targets based on increasing distance, and then chooses the targets that have scores increased. Far targets have scores decreased, okay? And when the selection is made, the target with the highest score is selected, all right? Now, I don't know why or I suppose that, maybe in a game-like situation, or you're in an application where you've got molecules bouncing off each other, all types of crazy configurations, you need to select something. This is what you get when you've got moving objects around in the scene and you want to try to select one. So, as he moves the cursor around, we're doing this calculation basically every frame to try to figure out which object we should be selecting at any point in time. This isn't actually manipulating any object, this is just selecting objects. So it kind of just, you follow it and you just boom, all right, I've got it, because the algorithm basically says that that's the one that's closest to me, and it's fairly intuitive to do. Now, the next one that enhances the grasping metaphor is called intent-driven selection, okay? And the notion behind intent-driven selection is that you're going to use the posture of your virtual fingers as confidence levels in object selection. So what does that mean? Well, if you think about grabbing something in the physical environment, as I go to grab this water bottle, my fingers are gradually going to get closer to the bottle. I'm going to pick it up, okay, and I'll take a drink. So I have selected and I have manipulated, okay? So as those fingers get closer to the object, what happens is that you get these proximity spheres are positioned within the grasp of the virtual hand. So these spheres get smaller and smaller, and the virtual fingers actually, they're on the sphere, and anything within the sphere is selectable. So as the hand closes in, as you close in on selecting an object, additional proximity spheres show up, right? And they, as smaller spheres, and they basically allow you to select a subset of selectable objects until you get to a point where there's only one object left, because you're actually getting closer and closer to grabbing that object. All right, so it's a really nice way to enhance a grabbing metaphor by utilizing the fact that that you would be, in using your hand, you're going to be grabbing that way anyway. Okay, you're going to be using your fingers to slowly, grasp onto an object. All right, so that's grasping. Okay, now let's talk about pointing. All right, pointing metaphors. The pointing is very powerful in selection, okay? Because for one thing is that you can point it at anything in any distance and select it. All right, it's designed specifically for remote selection, but you can be done with objects that are closer as well. There's also less hand movement required, so it's not as much physical exertion you need. Okay, but typically, okay, pointing is not very good for positioning, especially when things are far away. And it's how you actually create the pointing direction, and the type of selection calculation is important. Now, when we think about pointing, we're typically think about vector-based pointing techniques, all right? And that is as simple as it sounds. You have a vector emanating from your tracking position, let's say your hand, and you're going to use that to basically do your selection. And there's a couple of different ways to do this. There's ray casting, there's a technique called fishing reel, and then there's image plane pointing. So let's talk about those. With ray casting, okay, that is the simplest approach. Okay, it is a very simple pointing technique. All right, you point at an object with a virtual ray. You have a virtual line that goes from that ray. You do a intersection test. Okay, very often this is represented as a laser pointer in the virtual world. Okay, the size of that laser pointer can vary if you want it to. You perform the ray casting, and then you actually select the object that you have intersected with. Okay, and you can be very precise in selecting faraway objects. So here's ray casting. So there's my ray, and I want to select something, and I simply just go ahead and select it, right? It's as simple as it possibly can be. And you also, the nice thing about it is you don't have to go to where that object is and use a grasping technique to pick it up. Okay? Now you could use the go-go technique, which works as well, but it's a trade-off. Maybe you don't want to use the go-go technique because it doesn't fit your application. The fishing reel is a little bit different. It's an additional input mechanism to the virtual ray, and the only difference with it is that you do ray casting, and then you have another component of your input device which can reel the object back and forth using a slider or a gesture or whatever. So you actually go grab something, and then you actually you could literally do this if you wanted to, like a real fishing reel, and bringing it in, It could be cool. I don't know. Obviously, if you're doing a fishing application, that would be pretty intuitive. Now, another fascinating technique is known as the image plane pointing techniques. And these are pointing, but they're done in a little bit different way. These techniques basically simplify object selection so that instead of actually selecting objects in 3D, you're selecting them in 2D, using simply a 2D plane in front of you. Okay? So you create a projection of the 3D world, and you stick it right in front of you, and you use simple direct touch on that plane to select objects in 3D. Okay? And it's typically used to manipulate orientation, not position. And these techniques include things called the head crusher, lifting palms, the sticky finger, and framing. Okay? And you may wonder where these names come from. I don't know where, the lifting palms and the sticky finger and the framing makes sense, but the head crusher came from a show called Kids in the Hall from HBO in the 1980s. And in that show, they would pretend to crush your head with these two fingers like this. And go, oh, I got you, And that's what they use as a metaphor for this technique. Now, we don't have that in this video here, but at least you're going to get to see what it looks like. So, no matter where the object is, okay, I can go ahead and select it because I have this plane in front of me, right? So even though objects are far away, I'm selecting from a two-dimensional plane, right, where the 3D objects are projected onto that 2D plane. So it's very easy to select objects this way, okay? It's a technique that's fairly underutilized, but I think it's really useful for selecting objects in three-dimensional space. Now, there are other variants to pointing. Okay, there's something called the flashlight technique, the aperture technique, and sphere casting. Now, one of the problems with ray casting is that when you have a lot of objects, or you have there's a dense set of objects, okay, or the objects are close together and they're farther away, the harder it is to use a ray and point at the one that you want. So all of these techniques tend to be what are known as soft selection techniques. So with the flashlight, what we do is we effectively instead of using an actual ray, we're going to use a conic section volume. Okay? So what that does is that gives us a region, a circle, if you will, at the end of the ray that we can use to do the selection. And that allows you to basically be a little bit less precise in doing selection of objects. Okay, the apex of the cone is at the input device. The object does not have to be entirely within the cone too, which is really nice. Okay, but of course the issue with that is, because it's soft selection, you have disambiguation issues, which means that you have to choose the object that's closer to the center line, if you will. Okay, sometimes there are different ways to deal with this, but that's one of the ways. All right, so here's the flashlight technique. And you can see the objects are really far away. It'd be very hard to pick one with a ray, but I can go ahead and pick them with the flashlight. I'm just choosing the one in the center. And it gives you that soft selection, so you don't have to be so precise, and as you move your hand you might start shaking and not be able to get that object you want. Now, aperture selection is an extension to the flashlight technique, and the difference is that the user can interactively control the spread of the selection volume. All right, and that's nice because sometimes what you want to do is your volume may be too big and you may be getting too many objects and having a difficult time in selecting them. So if you can change the diameter of the selection volume in real time, then that gives the user a little bit more control in their ability to do the selection. Okay, and you would use a hand sensor or something to change the actual size of that. Okay, and here's aperture selection. So you can see the ray or the selection aperture is changing. He's changing it dynamically depending on how he feels comfortable in actually doing the selection. Sometimes he may need a small aperture, sometimes he may need a large aperture. It depends on the situation. And sphere casting is similar to these in the sense that you define a position of a predefined volume at the intersection of the vector used for pointing, and you cast a sphere onto the nearest intersecting surface instead of a cone. Okay, it's very similar. Now there are, of course, enhancements for pointing techniques, bend cast, depth ray, and absolute and relative mapping. So with bend cast, bend cast basically is just pointing analog to a 3D bubble cursor. And what it does is it bends the pointing vector toward an object closest to the vector's path, right? So it literally bends the vector, okay? And it uses the circular arc to provide feedback to show you what you're selecting, okay? That's why it's called bend cast, because the ray is actually bent. As you approach an object, the ray actually will bend towards that object, right? Depending on how things are close to you. The depth ray is a nice example. It's when you've got, a lot of objects and maybe they're at different depths. It can be used to disambiguate which object the user actually intends to select when the pointing vector intersects multiple targets. All right, so what it has is a depth marker, which shows along the ray length, and then the object closest to that marker is the one that you want to select, and the user can control the marker by moving a tracked input device back and forth. So here's an example of that. So you can see the white cube represents that marker, and I simply use another part of the input device to cycle through the objects that I want. So even though I may have some occlusion, I can go ahead and simply use that extra piece of hardware, if you will, to select objects that are behind other objects. So it's a nice little technique when you've got more complex objects that you're trying to interact with. And as far as absolute and relative mapping, this is very useful in very dense environments, right? Really dense objects. Provides manual control over the display gain. And once again, we're thinking about non-isomorphism here, right? So basically, you can change the display gain ratio for the pointing, and it lets users increase the effective angular width of the targets. All right, and that gives the user the impression of a slower motion pointer, which can then help with selection. Now, there's a whole set of metaphors called the indirect metaphors, okay? And these ones, you're not actually selecting or manipulating an object directly, whether it be pointing or whether it be with grasping. You're actually using something else, a third party, if you will. And there's several techniques that do this, and they tend to build on each other. So indirect touch is the basic one, where basically you have a multi-touch surface as your input device to control a cursor on your primary display, right? And that display could be a VR display, it could be a television, whatever. And so you're using your one finger to actually move the cursor, and you could use an image plane to do this. And then with the second finger, you touch the surface to select the object under that cursor. And you use the surface-based technique for the manipulation, right? So the standard surface-based techniques, for pinching and zooming and so forth. Okay, and you can do absolute relative mapping with this type of technique as well. Now, this was extended to not just a surface on a smartphone, for example, but on actual surfaces within the virtual world. So it's an extension of indirect touch, and the mapping basically is a multi-touch surface to non-planar surfaces in a virtual environment, which is kind of cool, because it allows users to manipulate objects relative to desired paths along that surface or other objects. And you can actually draw along these complex 3D surfaces and then use those to actually tell objects how to move in space, which is pretty neat. Now there's the level of precision cursor, okay, which extends to indirect touch with physical 3D interaction. So using a smartphone, right? Smartphones give you multi-touch and 3D interaction with inertial sensors and with gyroscopes, for example. So you have that extra rotation, if you will. And you can map a smaller area of the smartphone to a larger area of the primary display and then determine orientation for pointing operations with the phone. Then, of course, there's the virtual pad, and the notion here is that I'm just going to put a virtual multi-touch surface in my virtual reality environment, and that surface is going to be used like a regular indirect touch input, okay? And it's similar to the image plane methods, okay, if you think about it, because what you're doing is you're placing a plane in place similar to image plane, and then you can go ahead and do your selection and or manipulation. Now, we've talked about a whole bunch. They're going to keep coming, okay, and I'm doing this because I want you guys to know that there's a lot of techniques out there for you to choose from that have already been developed, and you can look at them and you can use them, or you can derive from them, okay? So the indirect metaphors are metaphors for selection and or manipulation that effectively are using indirect means to select an object and manipulate it. And the two most classical ones are known as the world in miniature and Voodoo Dolls, okay? Now with world in miniature, okay, the idea is that you're scaling the entire world down to bring it within users' reach, okay? And so now what you have is a miniature version of the world, right? And this has its limitations, right? If you have a huge world and you try to build a world in miniature of it, it's going to be very difficult to select, right? You can have regions of that virtual world that you can create as a world in miniature, and it will work well. So you have to be a little careful with this in its implementation. But when you manipulate the object in the WIM, in the world in miniature directly, okay, or indirectly, you are manipulating the object in the real world, okay? And as I said, there's a lot of design decisions when it comes to world in miniature. But here's a video of it. So right there's the world in miniature, and when I select the indirect proxy, the actual object that I want to move, I can manipulate. So once again, I don't have to go there, right? If I want to be lazy, I can just use this little world in miniature, and I can move stuff around. I'm not sure what Puya is trying to do here. He's stacking furniture, I guess. But that's just a quick example. And the world in miniature is very similar to mini-maps in games. With this case, you're actually doing something with the mini-map instead of just using it as a navigational aid. Now, Voodoo Dolls builds upon the WIM, world in miniature, and image plane techniques. And the notion is that you want to seamlessly switch between different reference frames. Jason talked about these different reference frames. These different reference frames for manipulation, So you want to manipulate objects indirectly using temporary handheld copies of the objects, which are the dolls. And the user can decide which objects to manipulate by using the image plane techniques, right? So there's no scaling issues. And it's like a voodoo doll. Okay, and it's a two-handed technique. So the non-dominant hand represents a stationary reference frame, and the dominant hand basically defines the position and orientation of the object relative to that reference frame. All right, and the user can pass the doll from one hand to the other and do various things with it. Okay, so here's an example of voodoo dolls. So in this case, he selects an object. There's the doll. Now I can, interact with the doll. In this case, let's see, what am I doing here? Okay, I have to turn the doll around and then he'll move back and forth. And then you can go ahead and do whatever you want with it, but you're not actually changing. You're just using a little doll copy of the object that you want to interact with. So that's why it's indirect in nature. Now, this leads into the bimanual metaphors. Okay. And the bimanual, when you say bimanual, what are we talking about? We're talking about two hands, right? Two-handed manipulation tasks. And when we talk about two-handed manipulation and selection, we're talking about you have a dominant hand and a non-dominant hand. Okay, if you're left-handed, typically your left hand's your dominant hand, your right hand's your non-dominant hand. You've got symmetric versus asymmetric, and that means whether or not both hands are doing the same thing or they're doing different things. You got synchronous and asynchronous, meaning they're doing stuff at the same time or they're not doing stuff at the same time, okay? And examples of them, you can have techniques like symmetric synchronous techniques, where each hand is performing the same movement at the same time. Then you've got symmetric asynchronous techniques, where identical hand movements are done at different times. And then you've got the ones that are the most complicated, which are the asymmetric asynchronous, where different hand movements are happening at different times. And the quintessential example is pat your head and rub your stomach, right? Try to do that, right? That's pretty hard. That's why we try to stay away from the asymmetric asynchronous techniques, right? Trying to do different hand movements at different times can be somewhat challenging, okay? So there are several of these bimanual techniques. One category is the symmetric bimanual techniques, and the two that we'll talk about are spindle and isith. And the spindle technique is very interesting history. It was first developed by Mapes and Michel in 1995, and happens to be a technique that is used in the Make VR application that Jason talked about. Because that Make VR application, the previous version of that application was developed in part by the people who developed this technique. So there's a long history of this technique. And what it does is it basically takes two 6-degree of freedom controllers and uses them to define a virtual spindle that represents, that basically extends from one controller to another, represents the center of manipulation. And with that, you can, when you move both hands in unison, you can translate. When you can go back and forth to do rotation, and you can actually go like this to do scaling if you want. Okay. So here's a video of this. So I can scale the object, I can rotate it, and I can translate it. And then, yes, it's two-handed, but it's very intuitive to be able to do this type of manipulation. This technique also works very well for navigation as well. I can actually use it to pull myself through the environment. Or if I want to turn myself 180 degrees, I can go like this and go like that, and that will actually rotate myself 180 degrees. Now the isith technique is similar in that it's called the intersection-based spatial interaction for two hands technique. And once again, it uses two 6-degree of freedom controllers. They define two separate rays. You have ray casting on each with both hands. And the shortest line between the two rays is found by crossing two vectors to find a vector perpendicular to both of them. And that perpendicular line basically gives you a projected intersection point, or the point of intersection, which is used for selection. So let's look at isith. It's a little bit of a strange technique in the sense that, it seems to be overkill, but What it does is it provides much more precise selection. In this case, he's got the physics turned on, so the thing's rotating because it's only in one point of contact. But it very often depends on how many objects you have in an environment that you want to select, where they are, how big they are, how small they are, how many of them you have, are they moving, are they stationary, is there a lot of occlusion? All of these things come into play when you're talking about these bimanual metaphors. So a couple other ones. These are asymmetric bimanual techniques. There's the spindle plus wheel and the flexible pointer. The spindle plus wheel extends the spindle technique to include rotating pitch of the virtual object, okay? And it uses a virtual wheel co-located with a dominant hand cursor to twist for rotation. So it's a way to do more types of rotation with the spindle technique. The flexible pointer, which is really, really cool, it makes use of two-handed pointing, okay? But what it does is it creates a curved ray that can point at partially occluded objects. So using your two hands, you can actually take the ray that is emanating from the center of your two hands, and as you turn or move back and forth, you can actually turn that ray. Okay, it no longer becomes a ray, it's actually a quadratic Bezier spline. Okay, and so that way you can actually bend it around objects so that you can then select those objects that are occluded. All right, so now we're going to get to the hybrid metaphors. And these ones, they try to combine selection and manipulation together. Typically an aggregation of a bunch of techniques. The two we'll talk about are Homer and scale world grab. Okay. Homer, okay, stands for hand-centered object manipulation extended ray casting. That is a mouthful. But if you think about it, it's really very simple idea. Okay. You select an object using a ray casting. Then your hand attaches itself to the object that you selected, and then you use direct hand manipulation to manipulate the object. Okay? Extremely intuitive and simple. So let's look at this. Select something, the cursor goes to the object, I can translate and rotate it. All right? Want to do something else? Cursor goes to that object, right? Do the ray casting. Cursor goes to the object. I can do my selection and manipulation using basically direct manipulation. Very simple, very intuitive, very powerful technique. Now, scale world grab is another interesting one. And when I tell people about this one, they don't believe me when I say this, but it's true. It works. The math works out. What happens in this case is that the user selects objects with a given selection technique. It could be anything. But then what you do is the entire virtual world is scaled down around the viewpoint, right? So around the user's virtual viewpoint. And if the scaling is done properly, okay, the object now becomes in reach because you effectively are huge in the virtual world, all right? So the object actually just effectively is scaled so that it's right in front of you. And if the center of scaling is midway between the user's eyes, the user will be unaware that any scaling occurred, okay, which doesn't make any intuitive sense because it looks like the object is getting bigger, but it actually is not, right? It is internally, but from a perceptual point of view, you can't see it. So here's scale world grab. And it looks very much like image plane. All right, it's a very powerful, very easy technique. Not necessarily easy to implement, but easy to do from a usability perspective. All right, so we talked about non-isomorphism, okay, and we've been talking about, the trade-off you have between isomorphism and non-isomorphism. And we talk about non-isomorphic rotation a little bit because it's very important. And here's why. I take my hand, and let's say I want to rotate an object 360 degrees, okay, and I want to use direct manipulation. All right, I rotate my hand like this. That's 180 degrees, okay? Now, I could keep going, but as you can see, I can't. right? The physical anatomy of my body says I can't do this, all right? I could, but I'd break my elbow, and then what's the point, right? I'd be in the hospital, I wouldn't be able to do any VR work anymore, and then it'd be big trouble. So non-isomorphism effectively allows you to get around that, right? So if I double my gain, right, as I rotate my hand 180 degrees, but the object rotates a full 360 degrees, okay? So that's a very powerful way to do object manipulation with actually getting rid of the issues with anatomy, with the anatomical structure of the body that you just can't get around, all right? You can also go the other way, right, where maybe rotating my hand 180 degrees means I'm only rotating the virtual object 90 degrees or 45 degrees for that higher level precision rotation, okay? And there's different ways that you can implement this. It's absolute and relative mapping. This is a little more technical and in terms of implementation, but just to know that when you do absolute mappings, that violates something called directional compliance, which means that when you do absolute mapping, you can't, you don't know the direction in which you actually did the manipulation, okay? Because you're starting off at initial orientation 0, and you're automatically going to the specific orientation you're in. Relative mappings basically do deltas, right? So every frame I'm going to do a delta rotation, right? And that does not preserve nulling compliance, which means that I can't automatically go back to where I started from at the initial orientation. So there's trade-offs with each of these in terms of that you need to be aware of. All right. Now, we've just been talking about single object selection. What happens if I want to select more than one object? Okay, I want to do multi-object selection. Well, there's a whole slew of techniques for doing that. Okay, you could simply just select one object after the other, okay, but that's boring, right? It's not any fun. There's volume-based selection techniques, like the flashlight aperture and sphere casting ones, and you can adapt those to select more than one object. Then there's like defining selection volume. I can actually define a volume that I want to select something in, okay, like use 2 corners or a lasso on the image plane saying, all right, this is what I want to select. And then there's also volume selection widgets that you can use. There's also something that we call progressive refinement, which is sort of it's a fairly new approach to doing selection of multiple objects. And this gradually reduces the set of objects that you want until you get one or a number of them, okay? And you do multiple fast selections with low precision requirements, and there's a couple of examples, techniques for doing this. The first one's known as SQUAD. And SQUAD stands for Sphere Casting Refined by Quad Menu, okay? Once again, as I said, the names of these things are a little strange. This is known as progressive refinement and typically done in dense virtual environments, lots of objects. The user specifies the initial subset of the environment, okay, using a sphere cast. And then the selectable objects are laid out in a quad menu, all right? And then once you've got that quad menu, then you just use raycasting to select one of the 4 quadrants. Once you select that quadrant, then you get another quad menu with the elements in that quad. And you keep doing this until you get the object that you want, okay? And that works pretty well, but you have to keep going through this refinement. So the expand technique, something that my students and I developed, is similar, but the user selects a collection of objects in the beginning, and then you simply just take those objects and you build clones of them, like in the Voodoo Dolls technique, that come out to you. And then you just pick the one you want, okay? I'm going to show you a video of this. So it just gives me a selection of objects, and I can select the one that I want, okay? It's very straightforward. In this case, we've hard-coded the selection region. I mean, you could circle the region that you wanted to select, and then you would go ahead and get those, okay? Another one is called double bubble, okay? It's like a chewing gum. So both squad and expand suffer from initial selection. You start off with a large set of objects, but the 3D bubble cursor, as we've seen, is a really nice way to do initial selection. And the bubble basically is not allowed to shrink beyond a certain size. So you've got this bubble, and then objects laid out in the menu and are selected using a bubble cursor. So basically, you've got two bubbles you're dealing with. You take the one bubble that gives you, a selection of objects, and then you use a second bubble to actually refine your selection to select the one object that you want. Okay. All right. So that's a whole list of selection and manipulation techniques. Okay. Are they going to work for you and your applications? Maybe, maybe not. Okay. But here's some guidelines that we have sort of developed over the years that I think can be useful. First, if you can, use an existing selection technique that's out there already, okay? Because the fact is it's been done, it's been vetted, okay? But you may have to derive something from it for an application specific, if you have a specific application, one of these techniques may not fit precisely, okay? But at least it's there and starts off as a base that you can use for adaptation. You always want to try to use task analysis when choosing a 3D manipulation technique. What task are you actually doing? What selection are you doing and why? Okay, what's the reason that you're going through the process of doing that selection? And in doing so and coming up with that analysis then can very much lead you to the technique that makes the most sense. Okay. Now, ideally these techniques should work for every device, but that's not always the case. Okay. So you want to make sure that you match your interaction technique to the device as much as you can, okay? Some techniques work well with certain devices and some do not, right? And very often it's a question of trying to figure out what that is, and that can be a iterative refinement, all right? You want to try to use techniques whenever possible to reduce clutching, okay? Clutching basically is, I grab something, I let go, I grab again, right? Right, that's clutching. You want to try to avoid that. It's ergonomically not something you want to do. So any technique that helps you do that is good. Non-isomorphic, aka magical techniques, are very powerful and intuitive. I think you've seen that from the examples I've shown you. And if your application allows you to use them, then you should try to use them because they are very powerful. Pointing techniques for selection and grasping techniques for manipulation, that's kind of like a standard thing, right? It's much easier to point at objects and manipulate them using grasping, okay? But then again, you want to think about sensitivity when you're doing grasping because that's important, okay? You want to try to reduce the number of degrees of freedom if possible. If you're manipulating an object and you only need to move it along a 2D plane, then why do you need to do a full 6 degree of freedom interaction? Okay, it's a waste of degrees of freedom and only complicates things. So when you can, try to reduce the number of degrees of freedom. Okay? And with any of these cases, you're always considering trade-offs between design and environment, right? The technique design and environment design. There's a challenge between the two. And finally, probably the biggest guideline I can give you is there is no single best manipulation technique. And maybe that's something that you don't want to hear, but it is true, okay? Certain techniques work well for certain applications and for certain tasks. And as a VR, somebody who's doing virtual reality and is going to be doing selection, it's your job as a designer or developer or practitioner or hobbyist or whatever, you need to try to figure that out. And that takes iteration, takes refinement. Okay, so I just want to, just show you that what we just covered was just one part of one chapter in this book. We didn't talk about 2D or 3D surface metaphors for selection manipulation because, I wanted to stick with more immersive VR. We didn't talk about 3D widgets. We didn't talk about the case studies. And there's a lot of other things in the book that will be helpful. Human factors and HCI, background, input and output hardware, a whole chapter on navigation. I could have spent a whole another hour just on navigation, and another hour on system control. Okay, we could have made this a full day course if I wanted to. All right, and of course various aspects of 3D UI design. So with that, I'll leave you and have Rick Mark comes up and he's going to show you some really cool stuff with the Sony PlayStation.
Joe. Get switched over to my laptop. So I think we're at the end of SIGGRAPH here, last hour. I just had a triple espresso, so I'm good to go. I'm not sure about you guys. Anyway, I'm going to talk for a little bit, but then I have a live demo at the end, so if you stick around, you get to see the stuff kind of in action at the end, using some of the techniques actually Joe just talked about too. My name is Richard Marks. I work at Sony Interactive Entertainment, which most people know as PlayStation. Let me go into this mode. Okay, this is my 21st SIGGRAPH, and I've been at PlayStation for 18 years. So working on this kind of stuff, not exactly in VR the whole time, but interaction technology for a long time. A little bit more PlayStation-y look. I'm the only person on the panel that didn't write a book on this subject, so that's a bit of a dubious honor, but I'm going to come at it from a very different perspective, more from the industry side of things, and try to give you some motivation and some kind of actual real-world examples that we've put into practice. I run a group called the Non-Isomorphic Lab, right, Joe? Yeah, so no, it's the Magic Lab. It's what we do is we look at new technologies kind of through the lens of PlayStation, and we try to figure out how they might matter to PlayStation. And I guess a way I also like to think about it, there's a talk I saw a long time ago, which is about starting with why. And so when we look at a technology, we think, why would PlayStation care about this technology? And then how would we use it and what would we make with it? And then we decide to continue pursuing that technology or move on. So I think that philosophy works really well also for all kinds of research. And I'm going to try to motivate this whole talk with this kind of approach. So why is VR interaction any different than 2D interaction, or why is VR different than 2D at all? I'll just do a little section on that, just the high level why, and then I'll talk about things from kind of the point of view, again, more of an applied point of view. If you want to play with objects, you want to play with the world, you want to play with other people, and you want to play with virtual characters, how would you do these things in VR? And it's not going to be nearly as rigorous as these guys. It's, again, going to be more of a actual application-focused approach. So the big thing about VR, which I'm not going to spend much time on, is presence, feeling like you're somewhere else. And we talk about that a lot, but what implications does that have, especially for interaction? Well, the big difference is instead of being remote away from things, you're actually in among the things that you're interacting with, or the experience you're participating in. And so there's two kinds of aspects to that. Not only are you there with other things, but other things are in your own space too. And if you think about that, that's pretty huge. We've never been able to put objects next to people before, not the same way as we can with VR. So it is a very strong difference than with other kinds of media. And what ends up happening with that is basically the spatial and the directional cues are way more important in VR than they are in a 2D situation. When you look at something on a screen, you have to abstract out what all the spatial things that are happening. You get X, Y, but you lose Z, and you lose a lot of the angles and direction that are happening. In VR, if any of that's wrong, you notice immediately that it's wrong, and so it's much more important. So you have this kind of, when you're looking at the difference between 2D and VR being there among the things, actually, the first thing is size and distance matter a lot more than they would on a 2D screen. So when you see a dinosaur in VR, it's huge and scary and different. So size is pretty obvious. Distance is also very important. When something's far away, it no longer matters to you so much. Even if it's really an interesting thing on a 2D screen, in VR, if it's far away, you might not notice it. There's things like this happen. Big equals scary. Small equals cute. That just happens whether you want it to or not in VR. It's because you're programmed in to think that over many years of evolution. So you have to make your decisions a little bit more carefully because of these kind of inherent biases that people have. Actually, another thing that's, like I mentioned, close is really important to people. And I'm going to get into this a little bit more in a second, but there's a great example that these researchers did where they film this thing, and they wanted to do this empathy in VR, and there was about a person who's sitting there trying to decide whether they should commit suicide or not. And next to the person, you're sitting there, there's a cookie on a table. It has nothing to do with the story. This happens to be just part of the kind of set, and it's just sitting on the table. But people just came out wanting to know, and they tracked what people were looking at, and they spent a lot of time looking at the cookie, and they wanted to know, why is the cookie there? There's no reason the cookie was there, but because it was nearby them in the story, they got all focused on the cookie. So if you put any objects near the user, they're going to assume they're important, and they're going to try to do something with them. There's a great book, besides these guys' books, that I recommend highly if you're going to do any virtual reality work, by these gentlemen, that really gets into some of the psychology of VR and kind of the underlying design motivations, I think, that would help designers. So I mentioned this remote versus among, and one of the first examples that we had in PlayStation was this thing called bedroom robots. And it's just that you're in kind of like a child's bedroom, and you can look around and see the whole space. And there's lots of little things flying around and moving, and so it's kind of a magical looking world. There's these little robots that are doing things. When you look at them, it triggers some action, so it feels really neat. And everyone just sits there and looks around and doesn't do anything. But then you can tell them that they can actually lean closer and get their head right in next to the objects. And so once you do that, there's kind of like a little dollhouse. You can put your head all the way in, and then people get kind of a magical smile. They've never been able to get so close to something like that before. That's the really good part of this demo. It's one of my favorite demos, and it had a strong impact on me. Then the next thing every single person does is try to touch one of the little robots. And in that particular demo, there's no interaction. So you see this like big grin, and then you see this kind of crestfallen, oh, I can't do anything. So that moment where they want to participate. And that's the second big part of VR that I think is really important, is it's not really the ideal medium for just observing. I think it's much more interesting when you can participate. There's some other people that have found this, that just because you feel like you're present in the space, or you feel the need to do something, to be active. And there's a lot of other talks about this, and I've given a whole talk about just this subject before. If you look, you might be able to find that talk. The experience becomes very lean forward instead of lean back in VR, almost automatically. And especially for anything within arm's reach, you expect you should be able to interact with it. So one of the ways people kind of get around this issue is to keep things away from the viewer. If they can't interact, they just keep things far away. So something like 360 video, it's much better if you keep everything further away, for several reasons, but that's one of the reasons too, is people don't think that they should be able to touch it. Actually, there's a lot of interesting things around this that are related to your brain. There's actually a dedicated area of your brain that kind of fires when something becomes within arm's reach. And this kind of space has got a name. It's called the peripersonal space, things that are surrounding your body where you could grab objects and manipulate them. And there's a really interesting kind of side note, which is if you hold an object which has a reach to it, that space effectively grows in your brain, so that now you think a wider space is something that you could have agency on. So I think that's kind of a cool effect. And then another thing that's related to this is you have really good muscle memory in your own space. So you can reach over and know where something is, and you can remember, if I grabbed it here before, I should be able to grab it again. And that's important for some kind of things I'll get to a little bit later. And one of the ways that we can interact with things in VR is using spatial controllers. 6 degree of freedom controllers are kind of normal. I used to talk about this and was trying to kind of evangelize 6 degree of freedom controllers, but now they're kind of the mainstream, so I won't spend much time on it. But they're really good at making your visuals kind of match your proprioception, because it gives you these grounded in your own user space. Actually, Jason already talked about this, so I won't spend much time. So for PlayStation, we have 3 different 6DoF controllers. We have the DualShock, which is a 2-handed device. We have the PlayStation Move, which is bimanual controllers. And then we have the VR aim controller, which is kind of a specific device which you can point, and you can actually has analog sticks and things. But it's really good for kind of a shooting situation in VR. But all of them are 6DoF and tracked by the same thing that tracks the headset. So just a real quick side note before I move on. This kind of being among and participating in things gives you this kind of feeling like you're embodied in the world in VR. And that tends to encourage a more literalness aspect. So seeing something like a floating cursor starts to feel like a disconnect. That doesn't exist in the real world, so it's weird that you have flashing things, or, I mean, that doesn't feel like I'm really somewhere else anymore, because that just couldn't happen. And it depends on the situation, of course. Maybe if you have a very abstract experience, it would work. But some of the solutions people have come up for this is using something like visually consistent clues in the world. So in the heist, they just make anything you could ever interact with red. It's got a reddish tone to it. Then you know that that's something you could actually grab and do stuff with. You can make things make sound. We had this demonstration with NASA where we were on the Mars surface, and the rover comes by, and it comes up next to you, and it's very close to you, and people are looking around, and when its arm fires to move, people automatically immediately turn, because with spatialized audio, you can know where the direction of the audio is coming from. And so you can use these kind of sound cues to make somebody turn and look at something that you want to. That's another kind of natural way to do it. And then my favorite way is actually if you have a buddy in the world, a kind of virtual buddy, he can point things out to you and actually just talk to you and say, oh, that's a really interesting thing over there, and then encourage you to do it. And you feel like you're, really getting a real piece of information from a natural source. What I wanted to mention is, actually, if we all start wearing AR glasses and we see flashing cursors and like text floating everywhere, maybe all this will not be true anymore. Maybe now we'll just expect there is floating text and flashing cursors. So if everyone becomes more AR focused, maybe all the rules will change in the future, and VR rules will kind of fall away. I don't know. So, playing with objects. Joe just talked about this quite a bit, manipulation. So I'm going to just talk about it from a little bit more applied point of view. We first made in VR this demonstration called the castle. And it was one of the big moments for me when I really got excited about VR again. I'd seen a lot of VR in the past, but when I first looked at my hands in the castle demo and saw the kind of, you're supposed to be like a knight, so you see gauntlets, and they're specular and reflective and shiny, and they move in the light the right way, and you can reach out and grab things and pick them up and then interact with the environment. For me, that was like the big step that made me excited again about VR. But it comes from a long history of things where we were doing work in the same area. So I'm just going to show this video real quick. This is 2005 when we debuted the PlayStation 3, some behind-the-scenes footage first, and then we'll show you what we showed on stage. So we weren't sure when we were first doing this whether we were going to do augmented reality or virtual reality. This is just an iToy camera, and then it's tracking these colored objects, and then Eric Larson made this really great fluid simulation. Of course, this is 12-year-old real-time fluid simulation, so 12 years ago, didn't have quite the same compute power, but still, it's pretty impressive, and it's really a great feeling to do. It's really gratifying to pour these liquids virtually back and forth and mix them. So like I said, we weren't sure if we were going to show that in augmented reality. We didn't really have a game use for augmented reality, so instead we showed it in virtual reality. So this is a scene, like a kind of a bathtub scene, and you can dip. It's the same exact technology, but in kind of a virtual reality setting instead. But still, this is actually running just on a 2D screen. And there's other stuff that happens in that demonstration. There's cloth and things. So a little bit later, now we use this, kind of the same idea, but we're using the PlayStation Move controller, still on the PlayStation 3, still in 2D. I'm going to turn on the audio. Oh, I didn't plug in the audio. Actually, the audio doesn't matter too much in this one, but this is a good example of bimanual control with two 6 degrees of freedom, and actually the trigger controls the rotation speed like a lathe on the left hand. So you're you have like a tool in your right hand and an object in your left hand, and that's a really great kind of combination because you can manipulate the tool or you can rotate the object. And this is Anton Mikhailov who's showing this, and we made another demonstration. Again, you could do augmented reality, but also virtual reality kind of version. We thought of it as virtual reality even though we were doing it on a 2D screen. And so he's going to switch into kind of the VR mode instead here. Again, with 6 degrees of freedom, you can do all sorts of twists and rotations and things. And the same kind of thing that Joe mentioned where you can stretch and so, yeah. So on the PS4 and in virtual reality, one of the great examples, I think, of bimanual interaction is the London Heist. And I'm going to show that, and I'm definitely not going to play the sound on that one. It's not fit for work. But yeah, so the London Heist is from our London studio. They had a lot of experience with cameras. They know a lot about how to use the PlayStation Move controllers as well. So they hit the ground running, and it was one of our most popular demos, and I'll explain why at the end. But you can see, you look down, you see these kind of nicely rendered hands, which are gloves. You're supposed to be a thief, so you have these kind of leather gloves. You can reach out, you're in a car, you're not driving, he's driving. You can pick up objects. This is one of the experiences which is in one of our bundles that comes with PlayStation VR. You can reach out and turn on the radio, and yeah, almost every, like I said, you can see it's kind of got a red thing near it. I'm not sure how well that's coming out on the screen, but and so this game gets, a little bit more intense. There's at some point, yeah. So you eventually get a gun and you do some kind of two-handed interactions. And let me talk about that here on this next slide. So why was that scene so popular? With most of the people who tried that demonstration really got excited about VR, and especially the gamers. And I think it's partly because, first of all, you're sitting in a chair doing this experience. In the car, you're sitting. So you have this matched affordance. You feel like you're doing the same thing with your rest of your body. The controls were really simple, just one trigger for each hand, just a grab. That's all you had, and very literal grab. It's very busy. There's a lot of things to do, and it gets to be very intense. There's kind of this fight or flight, if I don't do something, I will die kind of situation, and that kind of raises the stakes. There was a talk about this at SIGGRAPH a couple days ago, and about how having high stakes makes you more engaged by the limitless people. There's lots of interactive stuff within arm's reach, so there's all these things you can do, like the dials and things, and you can actually open the door of the car. And one of the really interesting things, I think, is when you go to grab the dial and you turn it, when you grab, your hand actually moves into the reference frame of the dial at that moment. It actually it does it seamlessly, transitions, but now all you can do with your hand while grabbing the dial is rotate. There's nothing else that hand can do except for rotate in that one axis. Same thing when you grab the little thing on the glove box or the thing above the windshield. After you've grabbed it, you're constrained to the degree of freedom that the thing you're grabbing has. However, when you grab a free object, then the object moves into your hand, and now you still have one-to-one mapping of your hand during that time, and then the hand pose conforms around that object, so they have to do special animations for each object. So it's a little bit of extra work, but I think it gives a really great effect for when you're interacting with things. So there's a lot of bimanual interaction. You can pick objects up and you can switch hands with them, but you also eventually get a gun and ammunition, and the real only way to load the gun is to have one hand have the ammunition and the other hand have the gun and put them together, so you have to use two hands together. And there's other things. People get really good at using their hands together. There's a door where you can open up and lean out, and so people hold the door open, otherwise it closes, so they're doing multiple things with their hands at the same time. Another thing we learned while watching people play is there's a kind of a stash of ammunition to the side of you, which at first you look at it and everyone looks at it and sees it, but then after a while they don't even look anymore. They just reach over to where the ammunition is, grab it, and expect it to be grabbed by their hand. They just reach into this kind of bag that's next to them and pull out ammunition. And so if you're thinking about designing like an inside-out tracking system where you only have tracking of your hands where you're looking, that would fail. You wouldn't be able to see your hand if you reach over there. So actually that could be a kind of an issue for some of the new tracking systems, I think. But there's a lot of things that I think that work there with the object permanence as well. First of all, you can reach in and you know that something will be there. You hear audio cues constantly. The driver's constantly talking to you. That makes you feel like it's always there. And the car door also, you can reach over and grab it and open it without looking at it. So those kind of effects I think are important to implement, not just things that are on screen. That makes you believe in the world more. And the last thing, which is kind of classic for all games and works really well in VR, is you do something small and it turns into something big. In this particular game, you can shoot the tires out of the cars and the motorcycles, and the thing will flip up and do a big, giant explosion. So you do this very small thing, and it turns into a very huge thing. And that works well in general, and that's why I think also physics works really well in VR, because you can kind of do a small thing, and the physics amplifies it into something large. So one more quick thing about manipulation. I don't, unfortunately, have a video of this experience, but it's one of my top 5 experiences ever in VR. This is again Eric Larson, but he'd moved on now to do some eye tracking. And this is a headset that had eye tracking integrated into it. We haven't talked about this because it's more on the research side, but basically it uses one of the techniques that Joe mentioned, and you use eye tracking for selection, and then you use a go-go kind of hand for manipulation. So you just look at something and reach out. You actually don't have to reach out. You just squeeze with your hand, and now you have the object no matter where it was, and then you can manipulate it. And so you can kind of throw objects up in the air and then just grab them out of the air kind of magically, because your eyes are looking at the object and then your hand grabs it. And then once you have it, you can pull it into yourself and then throw it somewhere else. And you definitely have the strong feeling of levitation. And this particular demonstration he did with 2 people, so you can actually throw things back and forth to each other this way. And it feels like a wizard's duel. I mean, you can just be picking up giant objects and hurling them at each other, but you can just pluck them out of the sky and throw them back effortlessly. And it's a really good combination of those techniques that Joe mentioned. Just basically a ray cast from the eyes and then the go-go hand of the hand. So, before I leave this, there's a few things that are worth mentioning. Current VR headsets have some kind of divergence and accommodation conflicts, and actually when you're doing things in your nearby space and look at them closely, you can sometimes have a divergence and focus kind of conflict. So that's one thing to think about. If you're going to be bringing things in close to you a lot, you have to be a little concerned about that. And another thing is haptics. A lot of the different solutions, they just kind of start to break down when you don't feel what you're doing. I think having an actual trigger or kind of something you squeeze helps a lot with haptics. And I think this is an area that's super ripe for research, and I think this will really take off in the next few years in VR. But right now, there's still a lot of things we can't do well haptically. And there's a lot of different companies looking at some of these. We've looked at some of them ourselves, and so this is a company, Tactical Haptics, that we did some research with, and just looking at bending and grabbing and the feeling of object heft. And it's a pretty neat kind of feeling when you feel the forces in your hands. But yeah, I think this is an area that's still got a lot of space to work in. So, locomotion. Playing with the world is a different way to think about it. So, moving through the world. There's a lot of options here. I'm going to skip through them quickly, but one thing that people have done a lot with is just leaning with your head, moving your body, kind of just this very basic move forward, move backwards, Segway kind of motion, I think some people call it. You can use the gamepad, traditional gamepad. You can use analog sticks, or you could actually use the motion or 6-DoF tracking of a lot of the gamepads have. You could have a dedicated controller like the aim controller I mentioned. A lot of these things work really well for certain experiences. Something where you're flying in a ship. The Electronic Arts show that their Star Wars experience for the PlayStation using the DualShock controller, and it feels great flying that with a regular kind of analog stick controls because you're in a something that would fly that way. But what we focus mostly on our lab is how would you do locomotion with hand controllers, these bimanual controllers. And so here's a blast from the past again, where Anton is showing what you can do with the PlayStation Move, and this one I do need the audio. Here it is. Is that coming through? Yeah, I think it is. So this was a very particular game.
This version of what you might see in a 3D environment. So here I actually have some chameleon hands and some branches, and I can use these hands to reach into the scene and move around these branches. And this is a really intuitive way to navigate 3D space, especially when you have to move around a large unstructured environment, something where you can't necessarily decide for the user where to jump or where to move to. You can just, jump to this branch or jump to that one, and the game has no idea where I'm about to go. And in 3D, this is also very compelling because you get that extra depth perception. Since the move tracks in 3D, it's going to be a very powerful combination to combine this with a 3D display.
So anyone making a chameleon game, this is the perfect interface. And this was on a 2D screen, but actually in VR it works much more intuitively to just see the things. And again, if you're going to make something like a Spider-Man game or something, I think that would be a great kind of metaphor for this. So we've done some kinds of experiments with this. You can do this one-handed grab where you grab the whole world. You can kind of swim through the world by using two hands, kind of like Anton was just doing. You can do these different things that Joe mentioned where you can you can treat the world as if it's an object, basically, and you can scale it down, you can scale yourself up, depending on how you're thinking about it. And one thing that's really interesting when you're doing this is the player focuses on their hands while he's doing this. So actually he stays in his own reference frame where his hands are. So even though the world can be doing kind of crazy things, actually it generally turns out to feel okay because you're focused on what your hands are doing and you're still looking at your hands while you're doing something with them. Another interesting thing is what you do with momentum when you let go of the world. Do you end up flying through the world, or do you just stop rigidly where you were? I've tried this really great game by these people that made a thing where you grab with both hands and you just throw yourself through the world and you basically jump to the next place. And it feels really good. They did a really good job of making the physics feel well. So that's another way, just kind of launch yourself through the world with this grabbing and then physics. There's some other kinds of things you can do, which is a little bit simpler, where you just point in a direction and use it as a thruster. So it's either going to shoot out the bottom of the controller or it's maybe going to pull you in the other direction, like a reverse thruster. You can press a button and just jump a short amount, like a mini teleport in the direction that you're pointing. Or you could have something where you have it more like a grappling hook, where you point and how long you hold the button basically shoots out something for a certain amount of time, and then when you release it, you get pulled there or you teleport that far maybe. So you have this kind of variable teleport that way, without actually having to necessarily render any kind of ray like the other teleport, which I show here on the right, just the regular kind of ray cast, or the one that the Vive uses or other games use where it has more of an arc to it. So there's a lot of ways to do teleport, actually. Joe already mentioned this world in miniature, and I'm just going to skip right to what one of the members of our team did in a hackathon. Just in a couple days, he implemented a world in miniature, and I'll just start the video here. It's a little bit hard to follow. He's looking around. So this was like a Matterport scan of the hackathon environment that you're standing in VR, and then you have a world in miniature of that hooked to a little stick in your other hand. So again, you're doing bimanual interaction. You have one hand that has a mini world, and in the other hand, you have this little tiny hammer. And this little tiny hammer can reach into the world in miniature, and zombies start to attack. And when you hit one of the zombies in the world in miniature, a giant hammer comes down and smashes the zombies in the real-sized world that you're in. So it's kind of a powerful metaphor always to have the miniature world, and having it turn into a weapon makes it even more powerful. So yeah, just I guess a real implementation of that for a certain experience. So finishing up on locomotion and playing with the world, Joe already said, you really have to match it to the experience that you want. There's lots of room for creativity here. This is not it's not really necessarily a problem. Everyone talks about locomotion being a problem. It's actually kind of an opportunity. You get to be very creative. And I think people have a way to stand out in this area still for certain applications. So that's an exciting thing about it. So I'm going to talk about playing with other people. A little bit higher level kind of interaction. Interaction we think of it sometimes at a very low level here, but real interactivity is, how we interact with other people mostly in our lives. That's what most people would define as interactivity. So in VR, we have several different ways. You can do it asymmetrically, where one person's in VR and other people are not. The Playroom VR experience that comes with our headset for free as part of the package encourages this. So you can have people on the couch playing with you, even though one person's in VR. There's a shared space VR or location-based VR where you have multiple people in one space, all in VR together. And there's some great exhibits here at the eTech of that this year. Actually, one of the coolest experiences I ever had was when I did that with my son, and we're in this kind of, again, like a combat space, and you're standing physically back to back, and it feels very realistic because you can feel the other person there kind of guarding your back physically. So I think that's a great thing. But really what I'm going to talk about is the kind of more traditional one that most people talk about when they talk about interaction in social VR is co-presence. So over a network, feeling like you're in the same place even though you're not. And there's some great games already doing this. We first showed this back in 2014. We took that castle demo I mentioned and just quickly made a two-person over-the-network version of it. And it was really insightful to do that. We just wanted to have two people for the Tonight Show to do it, but actually we learned a lot from doing that, and we went on to do some other experiences working with NASA. First of all, the hands and the head provide a very rich feeling. When people are there, you can really get a strong impression that there's another human on the other end of it. The toy box experience that for Oculus is one of the classic ones that helped with this. Another thing we learned really early on is that having spatialized voice and some extra gestures really adds to this kind of co-presence. Same thing that I think that a lot of people experienced when they tried the toy box from Oculus. We did this thing with NASA, which is two robots, and we showed this at SIGGRAPH 2 years ago here at VR Village. And the really strong part for me was when you actually picked something up and held it out and handed it to another person, and they actually took it right out of your hand. And that was a really strong, compelling thing, but it's very hard physics-wise to make it so two people can kinematically kind of hold an object and then share it. So it's still not a completely solved problem, I think, to have two people working together on things and handing them. I know that like High Fidelity has been working in this area, but I think it's still not easy to do. One of the things that we realized when we made that experience is the actual overall experience we made wasn't super compelling VR by itself. The graphics weren't all that realistic, but what happened was when you're there with another person and they point to something and say, could you get that object for me? And then you pick it up and hand it to them and they take it. You start to really believe everything that's happening is real because the other person is kind of like a witness to it with you. And you get this kind of loop where their social behavior is reinforcing that the world you're in that's virtual is actually more real than you would otherwise think. And pretty soon, this kind of cycle, and the same thing is if they point to an object and say, can you get that for me? Then they're seeing the same objects as you, so they must be here with you. So you start to believe they're actually here, and this is all real because of this kind of reinforcement. So we wanted to try to make that better, so we looked at another. I'm going to go through this one a little quicker. This is a two-player experience. We just wanted to make the person look more realistic and be able to be fully represented in that space. So have a full body instead of just these kind of often you see floating hands. And so this is a third-person view of the player, and you can switch it to first person, which it'll just do here in a second. But really maybe, yeah, so this is more classic kind of first-person way you would experience it. You can see that. And all we have is head and hands here. But I'm going to show this video here. So this is the two players playing And it's just the head and hands being tracked, but because it's a constrained situation where we know the person's standing like on this virtual pedestal, they can't really walk. So when they lean or they duck or they jump, you can really represent all of the degrees of freedom of what's happening pretty well. So if you constrain the situation, you can actually make the representation look more realistic. What we also discovered is you could actually have a pretty interesting spectating kind of situation here because they do look interesting to look at. The game Farpoint uses the gun controller, and since your hands are in a known configuration on the gun, it's, again, a constrained situation. So you can do all the IK very well for the whole body because you have this known constraint of where the hands would be on the device. And then, this is kind of a side note, but it's also getting very popular right now to add views into the virtual world with your phone. And so you can do this asymmetric thing, again, by having a phone as a screen that you look through and see the virtual things happening. So beyond head and hands, there's still a lot of things that we don't have representations for. Eyes, fingers, facial expression, a lot of other things. So there's a great talk by Ellie Shapiro from the Game Studio group, which is about how to make up some of these things for a social experience. And so she does something with eyes automatically, and she does something with kind of facial expressions unless you control them. I recommend that if you're interested in social VR at all. But my group's more focused on the actual real gathering of the data. So we did some VR hand tracking work early on, and this is also getting very popular. There's a lot of different companies working on this now. It gives you a really strong sense of your own presence, and it's nice to see somebody else's hands. You can do really great communication and gestures. I actually put the hand tracking research here in the social part because I think it's at least as important for social VR as it is for actually manipulation or something like that. But the area that I think is the most exciting for me is, again, using the same eye tracking. This is actually the exact same demonstration I mentioned before, but when you see the other player, his eyes, since they're being tracked, are also represented in his avatar. So here you can see, here's the other player. We're watching him. He's looking around. And you'll notice when his eyes kind of move in a much more realistic way. They're not just rigidly attached to his head like they would be. And so one of the things, let me stop that for a minute. Right before we end here, he's going to very subtly look at his own hand, and his eyes just very slightly narrow in on his hand. And we have really strong skills at noticing these kind of things. So I can really tell where somebody's looking by their vergence and things. So here, I'll continue this on. You can see just at the very end, when he looks at his hand, it's just a lot, I mean, the whole thing suddenly feels like there's a person there instead of this kind of, I don't know, fake avatar thing. So I think that's an area that's really going to improve co-presence when we have real eye tracking integrated. For now, this is currently just research for us, but it's an area of future interest. So I already mentioned this reinforcement loop. When there's another person in VR, it's this great amplification of the whole presence feeling. So my group was wondering if we could get that same feeling when there's not another person there. There's some other groups that have looked at this too. The London Heist, I mentioned, has an interrogation scene where there's a virtual character and he gets right up in your face. And it's very intimidating. The Playroom VR people, they made the bedroom robots, and they also made another experience called Magic Controller where there's a little robot and he's looking at you and pays a lot of attention to you. So he really feels like you're sharing the same space with him because of the way he reacts to you. And there's some other great experiences that I recommend. Gnomes and Goblins is a really good one for this. On the, I think some, I don't know what headsets that's on right now, but, and then in Japan we have this experience called Summer Lesson, which has got this virtual female character, and she comes and she sits down next to you at one point, and for me that was an extremely strong moment. I realized completely she's a graphical character, but having somebody kind of sit in your space and behave somewhat realistically was a very compelling feeling. So we went on to investigate this a little bit more, and we have this experience, which I have here today to show you guys at the end, with these little kind of robot characters that react to you. And they try to react in a realistic way if they were sharing the same space with you. So what that means is they react to the environment, but they look around in a kind of way that makes sense. Their eyes move quicker than their head, and their head moves quicker than their body. They also don't see things that aren't within their field of view, and they blink realistically. But kind of in a more important sense for VR, and what Jason was saying earlier, is that they really do the right thing for the player. It's a very human-centric thing. They should react to you the way you would expect. If you make a noise, they should turn and look. If you wave, they should turn and look. If you point at something, they should look at what you're pointing at. And also I mentioned the environment and other NPCs, but if you look on this page, the player is a huge portion of what they need to react to. So I mentioned if you make noise, or if you wave, if you point up, I don't know if you can see that, but if my virtual hand's pointing up at the ceiling. Also, if you look at them and then look away, they'll turn and look at what you're looking at now. They're interested in where you looked. And then if you stare at one of them, they'll hold your gaze. They won't just look away, because once you show that you're interested in them, they stay interested back in you. So otherwise, if you're not looking at them, they'll look around and do whatever. But if you kind of get their attention and look at them, they'll stay connected to you. So I'm going to switch over to the demonstration here, and hopefully this all goes well. There we go, test, yep, all right. That was the easy part. And, oh, we got it on the screen, we got audio. I think we're good to go. Now it's just the VR that has to work. So this is a really simple demonstration. The code for the behavior is not very complicated. The rules are really pretty easy. Hand switched. So I have these virtual hands, which you can see. You guys can see this? All right. And so I'm going to try, if I'm talking, that's why they're looking at me. If I stop talking for a second. Hey. Oh, you heard the train whistle? That's distracting to them sometimes. And so, again, if I'm talking, so it's going to be hard not to keep their attention, but I want to keep their attention anyways. I'll point at the ceiling. Hey. And so that's the main purpose of this. I mean, they just feel like they're sharing the space with me, but they are a little bit far away from me right now, so we added another little part to this, which is interesting, I guess. So I'm going to point at maybe the soccer ball over there. You can see he's pointing at it too. He's kind of saying, do I want him to get it? Okay, yes, go get it. So this part wasn't really the main point of the demonstration, but it does bring the robot up nice and close. And so now you can get right here. You can see he looks at me, and I feel like he's actually here because we're doing this. He's sharing the space with me, and they care about the same things. They react the way I would expect. Hey, stop it. And so, since we're all here and watching this, I'll show one other part of this demonstration, which is also, if you switch the character out, it gets a little different. That person actually, looks kind of scary. And they still can follow the same rules. And we didn't do much with the animations here. It's very procedural, animated, and programmer animated, but yeah. So they just feel like they're more connected to you. And then we had one more character. Look at that. All right, so, yeah. So actually, that last part, when I pointed an object, we first did a ray cast, but people aren't very good at pointing, so we switched it to a flashlight technique, actually, because it works a lot better at selecting things. So some of those things actually end up mattering when you try to implement these things for real. Real quick, if we go back to the slides for one more thing, we actually have we're taking some of that same idea and we're going to show it at an upcoming conference. Oh, this is Hey guys! Oops. Sorry. Switch the video back. Oh yeah, that train whistling in our lab every day for a long time. It's our favorite sound in the world. So, have it there. Oh, there it is. Okay. So, yeah, we're going to take all that same exact thing. Hey, guys! And so now, if you had something like cameras on your VR headset and you could see the real world through the cameras, and then that video could also be processed so that you see faces in motion, and then they'll react to the things in the video as well that is from the headset, then you can do something like an augmented reality version of all that same stuff. So that's future work and research area, not really at all product area, but something we're really excited about for the long-term future. And that ends my talk, and I thank you all for staying this long, and thank you very much. And I think all of us are happy to answer questions here. I'm mic'd up, so I'll step away from the mic.
Oh, beautiful talk. This is the long-awaited talk of all of SIGGRAPH for me, and thank you. Thank you, guys delivered in spades. You guys are absolutely thought leaders and pioneers in VR altogether. Richard Marks, you happen to be in a very unique position to actually have almost influence on the hardware that kind of limits a lot and creates the UIs that all of you spoke about. And you mentioned kind of the disruptive stages, right, of VR, where there was VR, and then you played the castle, and you saw the next level of VR. If you guys wouldn't mind, maybe just do like a thought experiment where you can set the stage of the next disruptive stage of VR and what UI and what what you guys would think about that.
So it's an area that we're looking at a lot of different things in, I think. So my answer would be just a general area of things, and they don't in any way represent what might happen for our hardware or something, but we're excited about eye tracking. We've been excited about eye tracking. It gives you a lot of different things, foveated rendering and lots of other things like that. Really excited about what haptic technologies are being shown here at SIGGRAPH and in other places. And really excited about the idea of all that same tech that gets developed eventually finding its way out into augmented and mixed reality kind of applications as well. So maybe I'll end with that, yeah. You guys want to answer?
Yeah, I have some thoughts on that. So, yeah, there's certainly a lot more we can do with VR. You've seen some of out in the exhibit, some like full body tracking and such that is just absolutely amazing. That takes that social interaction is just amazing, like how sensitive we are to human motion and such. So one thing we're proposing to do, hopefully starting by the end of the year, is not only doing that full body tracking similar to what they're doing out there, but Richard mentioned haptics. There's actually very simple solutions to haptics, kind of, dumb simple solutions, right? That can be extremely effective. As I mentioned, the physical objects in that world, reference frames, if you can map those to the visuals and suddenly set up an entire physical environment that matches the visuals. And when you can reach out and physically touch things just exactly like they are in the real world, then your level of presence just goes to an entire new level. Now, I don't know if that will be anytime soon in people's homes, but for VR-cades, in our case, for sort of enterprise training and product prototyping and things like that, then yeah, that gets me really excited.
I think the next, really for me, the next thing is as simple as simply just the next iteration. If you take like the next level of HMD that's affordable, that will come out, that will have 4K resolution per eye and so on and so forth, and combining that with 360 video, and the thing that I'm very interested in is VR cinema, and it's been quite a bit of discussion on VR cinema at SIGGRAPH this year. But interactive VR cinema, I think, is, and it ends up being very similar to what a game is, but at a level of fidelity, perhaps, that's a little bit higher than what a game can give you. So that's what I'm looking forward to and thinking about.
Beautiful. Thank you for sharing your vision.
Great talks. Has there been much research into having alternative mechanics within the one virtual world, so that, especially with people who are new to the idea of VR and struggle with a control mechanic, might be able to choose a simpler interface than someone who's been using it for a number of years? Is there much research into alternatives?
We're getting a lot of echo up here. It's
Shall I repeat the question? Has there been much research into having alternative control mechanics within the one space, so that people who are less comfortable or afraid or have a simpler mechanic than someone who's more of an advanced user?
So I think if I heard you correctly, alternative control mechanisms?
Yes, so
sort of thing?
There's been a lot of choice in the kind of mechanics that you can use in the interface, but that sort of implies that there is one way to do things. And so thinking back to like programming languages that, like the Perl days, where there's always more than one way to do things, and so different developers could choose different ways to implement ideas. So in terms of experience design, is there much research into how you can have alternative ways of interacting that might do the same thing, but in the same way as there's different styles of learning?
Yeah, so I would say multimodal input, right? There's a lot of different ways you can go about that. I actually had a slide in here I ended up taking out due to time constraints, which was, that slide was actually based a lot on Joe's work, actually, so he might have some thoughts on that.
Yeah, I mean, there's a lot of different ways to do a particular task or engage in a particular experience. I mean, just in the discussion on the selection and manipulation techniques that I discussed, I mean, right there in and of itself is a lot of different ways to do things. And I didn't even talk about how those things are implemented with different devices, right? So, perhaps somebody who's starting out in VR may not want to use a device. They just want to use their hands, right? And or maybe they do want to use a device that's similar to what they have already experienced. Like they want to use a mouse-like device because they've been using a mouse forever. So this one thing that I've learned over the last 20 years is that there's so many different ways in which you can do these types of things, and it's really important to have that user-centered focus, so that for those people who maybe don't have a ton of experience, or they can still be a part of it. And I have to go back to the example of when you talk about like the Nintendo Wii system, that was in part designed to bring a whole new class of people who were that's where casual gaming really came from. We have a whole bunch of people who are playing with this device that from a technical perspective, the device itself was very complicated to use and program for, because it didn't exactly do everything it needed to do depending on what it was, but it enabled people to do things very simply. So I think the mapping between device and interaction technique go a long way to giving you multiple ways of doing things that will tailor towards experience and people's abilities, and both at a cognitive and at a physical level. No?
I think you can also do, from the user's perspective, maybe he wants to choose something by pointing, but he might be able to take the same action by speech input, for example. And so thinking about, what is useful, you kind of have to be careful because, that complicates the system. And sometimes one modality isn't appropriate for another modality, but in some situations, maybe it does make sense to let the user choose the input modality.
Yeah, one thing I wanted to mention before was if you went to Real-Time Live, you saw the Unity VR editor, and it implements some of those techniques, and actually it implements multiple of them, and the developer can just use whichever one of those techniques at will he wants to use. So you can use the world in miniature, or you can use the world rotation, stretching kind of metaphor, and I think having those multiple options in the long run will probably be a good thing, where people can kind of pick the one they like the best.
Hi, I have a question regarding the world manipulation techniques. Actually, when you are pushing the world towards you for the locomotion, like with chameleon example, does it solve also the motion sickness, because you're sort of staying in place that the world moves around you?
For the world in miniature?
I think the stretching, grabbing the world as an object.
No, with chameleon example, when you're moving
Joe calls the
around
spindle.
the trees.
The spindle one, the spindle one.
Yeah.
I find that it helps a lot. I don't have any rigorous data on the subject, and I know that it doesn't solve it completely. Some people still don't feel great when you take the whole world and rotate it 180 upside down or something, but a lot of people are much more resistant to it, I think, than sticks.
So I was going to say, so I've worked a lot on that over the last, almost 10 years now. And so we've been thinking a lot about that and sickness. It seems intuitively it would be sort of a horrible thing to do, but it's actually not so bad as Richard mentioned, is if you think about it as if you're grabbing the world as an object. So you're stable, but you're pulling the world towards you instead of pulling yourself through the world. And so in some ways it's sort of the, how you think about it, your own mental model. We've also found things, for example, you can do a full 3D rotation, roll, pitch, and yaw, but that can definitely make people sick. Just by the world being tilted by 10 degrees can kind of make you nauseous. And so in Make VR, for example, we only allow rotation in the yaw direction. And the yaw direction, some people kind of feel it. We kind of warn people before they do that to kind of set up their expectation. But rotation in that case seems to kind of be the worst. But after they do it a few times, it doesn't seem so bad. I think sort of a real-world analogy I use for that is if you have a really large barn door that takes up your entire field of view. If you take that barn door and you move it with your hand, you feel like you're kind of pushing that entire visual field, but you're not going to get sick typically from pushing that barn door. There's sort of this connection between, if someone else moved the barn door, then you might have that sense of action, that sense of motion. But because we sort of have this direct connection of, in some way grabbing it with our hands, and our expectation is that we're grabbing it, it surprisingly doesn't seem that bad. But there's a lot of subtleties there you sort of have to experiment with and try different things. For example, I found for me personally anyways, is if I grab the world with one hand and rotate it, it can be pretty bad. But for some reason, if I grab it with both hands and rotate it, and I don't know why, but it seems a little bit better.
Another thing that's interesting with that technique is that it's great for something like a VR editor because you want to get around and do whatever you want to the world. It makes a little bit less sense, I think, to be in a VR experience doing that because you have too much power. However, For something like spectating, it's also awesome. So you're watching other people do a VR experience, maybe esports VR or something like that, and you can shrink the whole world down and look at them doing it in miniature, or you can stand right next to them and you can kind of, since you're not actually affecting the gameplay at all, you can use it, I think, there.
Yeah, and so that's one thing I didn't talk about in the slides is sort of what is the interaction fidelity? Are you trying to replicate the equivalent real-world action? In that case, you definitely would not want to use what Joe calls it spindle, I call it the world in miniature, Rick calls it the grabbing the world as an object, which I think is a really good way to describe it as well. But it kind of, again, the right solution, the right technique, like Joe was emphasizing, is it depends what you're trying to do. Right, so for realistic applications, it's probably not appropriate, realistic interactions. Although if you want to look at realistic scenes, it's like, you know, maybe looking at a map. But like a first-person shooter, that probably isn't the appropriate interface. But things like placing assets in the world, just like the Unity editor, it works extremely well.
Actually, that technique is also used not with the scaling, but with everything else, the rotation, in the Mission ISS, or I think they call it, where you're floating around and you can grab the whole station with your two hands and rotate yourself relative to the space station. So it's pretty similar if you're floating around in a space.
You know, in some ways, the interaction fidelity is low, but so we've done it with CT scans for medical data sets as well. So you can actually like pull yourself through the body and crawl through it, and you know, go in there with someone else and see them and such, point things out and all that. Just in some ways, it's kind of realistic because it's a CT scan, right? Like you're seeing the real, you know, someone's actual body, which can just be the, you know, the beauty of the body is just amazing. So the interaction fidelity is low because you obviously aren't going to do that in the real world, but the visual fidelity is sort of higher. So there's sort of these, you know, all these sort of continua that can, you know, you can think about the representation fidelity, the interaction fidelity, the experiential fidelity. And so one of the reasons why there's no simple answers when it comes to VR, but that's what makes it so exciting in my mind.
Another question?
Thank you.
Thank you for the great talk. And I would like to ask you to elaborate more on gesture input, which is, difference across cultural difference. And also, there's more ambiguous than the normal control.
Gesture input for what?
So I have a whole set of slides on that as well, and I think, yeah, it's very interesting. There's very different types of gestures. One way I think about it is sort of direct type gestures, which is that what the 3D multi-touch we were just talking about, because you're grabbing something and it's immediate, right? You just push a button to grab the world, and so it's sort of this one-to-one mapping of the gesture. There's no delay to recognize the gesture. It's immediate and direct. Other types of gestures, if you know, where you have that takes time to recognize it because it's a dynamic gesture, then, you know, a pose versus a gesture, gesture being typically defined to be more dynamic, over time, the system's not going to recognize it until you completed the gesture. And then there's, you know, camera-based systems versus controller systems, right? And the challenges of camera, you know, recognizing gestures, for example, or even if you have markers, it's not necessarily, it's pretty hard to get correct 100% of the time. So, you know, we can do pretty well 90, 95% of the time, but that last 5% is extremely frustrating. So in that case, I think you're fighting a pretty uphill battle if you're trying to solve general interface sort of problems with camera-based systems. But for like social applications, it's perfect, right? Those very subtle motions of the hand or the gesturing with the entire body is, you know, works extremely well for social applications. So again, you know, choosing the correct technology, the correct input devices, the correct techniques based on what you're trying to do instead of trying to force fit these specific patterns or designs or technology or whatever to maybe something that doesn't fit well. So really matching those things up like Joe was saying, and, you know, pick the best tool for what you're trying to do.
I'm not a huge fan of time-based gestures, so anything that involves a length of time, a path or something. But if there were more degrees of freedom input, then having more of a static recognizable gesture. So if you had, for example, finger tracking or something like that, you could have a lot more degrees of freedom quickly choosing something, I think. Maybe, but I think that's also challenging from a detection point of view. But I'm not a huge fan of something that takes a long time to do just to get something that you could probably have done a different way, quicker.
Yeah, one answer to that might be, you start recognizing the gesture, immediately, so you're at least getting some feedback, so you're kind of on the right path to, what the completed gesture might be one thing maybe to consider. Was there some specific use case you were thinking of, or technology?
Well, for example, like waving your hands. Some of the, well, maybe the meaning is like bye-bye or goodbye or, well, no, for example.
Yeah, I think those are perfect, like for social applications, absolutely. Those are, gestures are great for those sorts of things.
One of the things about gestures are both a blessing and a curse, because on the one hand, they do offer some very nice, intuitive interfaces. On the other hand, they're challenging to recognize, especially, we sort of break gestures down into poses, gestures, and activity, right? So you got the static pose, right? Gesture, and then actually some like running around, which would be the activity of running around, but that still can be considered a gesture. And then what you end up having is, unfortunately, gestures have different meanings depending on culture, application, so it can be challenging to know which one you want. For me, it seems like a lot of times, at least, gestures are going to play a very significant role in the social VR, social presence application. And the beauty about that is if you're communicating with someone else and you're doing the gestures, you don't need to recognize them, right? The other person's going to recognize them through traditional social norms, hopefully. And so that's where you can get that type of modality as a part of an overall communication dialogue within this social VR or social present type of application, instead of having to come up and do the whole rigmarole of doing a gesture recognition, which I've been doing for a very long time, and I can tell you that it's very difficult to get right.
Yeah, I think one of the big things about recognizing gestures and new modalities is that usually one is not just replace another one and be completely better than it. So each one of these different technologies, I think, is great at adding context to the others and constraining what you meant. So you said wave, and there's 3 different meanings for wave, but if I say hi at the same time, then it's very obvious I'm saying hi and not goodbye, or trying to shoo a fly away or something like that. So adding context, I think, is really great. Eye tracking, I think, is one of the greatest ways to add context. So if I say something, depending on what I'm looking at, it means something completely different. And I think same thing with pointing, same thing with grabbing, eyes, voice, all these things together really give us the richest interface. And trying to just do it with one is, it's going to be hard to get all the things we could get with all 3. So that's my opinion.
Yeah, and that gets, Richard and I were on a SIGGRAPH panel years ago where we talked about, actually, Richard really pointed out, buttons versus non-buttons, that was the question. And his answer was, of course, it depends what you're trying to do, right? And similar to gestures versus buttons. And yeah, maybe combining those in some way, right? You might do a gesture with a button press or a gesture with a voice, whatever that might be.
Okay, thank you.
Mm-hmm.
I'm going to go to something really simple in comparison to all of these richer schemes, but I'm getting clients that are asking for more and more branching narrative with spherical video using gaze-based dwell time and all that, and I don't know, there's kind of like a burnout factor that happens, I find, with like watching anything beyond 10 minutes and you having to do all that work. Have you found, there's a great piece, I don't remember the name of the company now, but basically every time you turn your head away and you look back, the scene's changed. You turn away again, you come back, their clothes has changed. I thought it was a really simple maneuver. Have you guys seen other kind of like more exciting approaches than just gaze-based dwell time, filling in a circle for just, positional cardboard-like experiences that are get us out of that format?
Yeah. Oh, go ahead.
So the 360 sort of space, single, button, and sometimes you don't even have that, so you got to go with dwell time, certainly constrains what's possible. And so it makes it pretty difficult to constrain when you have, a 1 degree of freedom input. And it's not even just 1 degree, it's, binary 1 degree, right? So, yeah, it's kind of difficult to innovate upon that. So I don't have a good answer for that, and that's been one of my frustrations with the lower end stuff. There's certainly some innovation happening beyond that. Like, for example, we're working with Merge VR and sort of low end, that's sort of a Google Cardboard type of add-on peripheral that is just, a fiducial marker that's used, in the AR mobile space all over the place, but they made it a cube. So now you have something physical, something tangible you feel in your hand. And now just by adding something so simple, that really opens up the design space of, allowing us to do really creative, fun things. There we go. Not quite. But yeah, you can imagine it's just a cube with markers on it so the camera sees it, and now you start doing gaze-based selection. For example, they have a very cool sort of Minecraft thing, but you're carving out cubes on the thing here. And we're working with them on creating a dinosaur excavation app, right? So you either touch in VR mode or AR mode, which is really a better fit for AR, sort of mobile VR, touch the screen and dig through the cube in order to dig up the dinosaur bones, sort of thing. So something so simple can add so much, just gives you that room to innovate.
Yeah, because I was saying, like, using the accelerometer or whatever, is there like a certain head, is there something that you guys have seen that doesn't require that kind of breaking of the immersion by, oh, I'm sitting here and I'm counting down and now something else will happen? I mean, is there a more natural way, I suppose?
I think Richard used I thought I saw you give a talk once on like head nodding and such.
Yeah, it's not great to make somebody move their head a lot, I think. That's one of the challenges, that just for a confirmation, constantly nodding and shaking and stuff. You can do it. Maybe you could get it to be very subtle, but for us, we have a pretty rich input scheme, so I haven't done too much effort. We've looked at using it to simulate walking. So if you just kind of go like this, you can get the head motion, and you can simulate footsteps forward and things like that. But anytime you make the head move, I think that's kind of more work almost. So.
Yeah, and especially on the lower end Google Cardboard sort of thing, you definitely want to reduce head motion because, there's latency and calibration and such there that, the more you move the head, the more the world's going to wobble around because it's not quite perfect. So that is one thing you want to be careful of, especially on Google Cardboard and such.
There is one thing that we did, and you need a camera, okay? I mean, so that's the thing. If your Google Cardboard or your device has the ability to get to a camera, and you can just look at your fingers, right? And, instead of this dwell time, I mean, the whole dwell interaction metaphor has been around for a while. They used it with the Kinect, and nobody likes to sit there and dwell, okay? But so one of the things that we did is we compared it to just simply, numbering a menu system, 1, 2, 3, 4, 5. Give me number 2, give me number 4. And you just recognize how many fingers I've got holding up. And it worked so much, it was so intuitive because it was just, you just look at the number and you say, oh, there you go, all right? So that doesn't require a lot of extra innovation. If you can actually drill a hole into the cardboard so that you can get the camera, and then you have access to the camera, and you don't even need a depth camera to do it. You can just do, you know, simple edge detection on your fingers. As long as you have your hands out at a reasonable plane, you'll be able to tell how many fingers I'm holding up. So that's one thing that we've done that was pretty successful.
Another thing I haven't seen a lot of, and I don't know why, but is, well, I'm sure because there's a lot of noise, it's difficult to do right, but voice recognition, right? So that in general, that's hard, especially on a low-end device with a lot of noise in the environment and such. But if, you know, like Joe's saying, if there's only, you know, 4 options, you can say 1, 2, 3, or 4. It works on, I personally don't like it when I'm talking on a phone and talking to, you know, but maybe it's less frustrating than dwell time. So I'm surprised I haven't seen sort of voice
that
interaction more.
is interesting because, you know, you've got Siri and Cortana and all these devices, and speech recognition is kind of one of these things that's kind of a solved problem, you know? I mean, people have been innovating longer on that than they have in VR, and that's why, you know, say, what's your problem when you get on the phone? And I of course, never want to talk to the computer. I want to talk to a person, but so you would think that there would be more interfaces that required speech, but it's been my experience, I don't want to have to talk to the computer all day. You know, if it's something that's done a little bit here and there, it's fine, but if it's the main modality, I just don't want to do it. And then you run into problems when I want to talk to someone else, and then it thinks I'm talking to, you know, then you have to talk to it by name, and, you know, it's like, okay, Siri, you know, it's not as natural as other potential ways of doing it, I think.
So not a complete answer, because I'm not a big fan of talking with computers either, but as far as, you know, if you have that clutch of saying, you know, pushing the button to push to talk, essentially, it, you know, somewhat helps with that, or maybe making a gesture and talking, right? This, whatever it might be. Again, getting back to the multimodal input, I think there's a lot to be done there, a lot to innovate upon that space that we don't necessarily know the answers to yet.
Thank you for that. You know, in the end, it's just that the gaze stuff, it requires that your head can actually move a certain, you know, sometimes you end up with your chin in your chest, or you're lying on your bed, and it's just really, it's clunky, and it needs to be updated, so thanks for
Yeah.
More, I guess, if there one more question, if we have time. On Karim's point, there is a demand, right, for sort of not the peak, right? Right now, the SIGGRAPH, all these conferences are really focused on pushing the outer limits, right, the higher limits of VR, adding voice recognition and haptics and eye tracking. But still, if you look at film festivals, right, if you have a narrative 360 video with even one decision tree in it, you're guaranteed to win, right? Nobody even has that. And that's very simple technology. I mean, that's almost like the trough of, or the valley of the peak that we're all aspiring to, and that you guys write about. Talk about, I guess, the, you know, quantity over quality, or essentially this stage where we are, where it's almost underserved for even the low-end experiences, right? Even like we talked about the simple 360 narrative, right? Video, even that, there's not enough of that, right? There's not, people demand more. If you look right now at SIGGRAPH, the VR theater is sold out every day at 8 a.m. for the next day. So if you guys can just talk about, I guess, anything we've skipped in our search for bigger and better, faster VR.
Yeah, I think, so I talked about the crazy high-end sort of, you know, full body tracking over, you know, large tracking space and such. But I think really, so that's one way to, you know, where I'm really excited about. But also just, I mean, it's so early from a creative standpoint. I mean, obviously, you know, we've been working on, lots of others have been working on VR for a long time. But to be honest, more from the technical side, even though this is kind of a human-centered design sort of presentation, we're kind of new to that space, right? Everyone's new to that space because before, you know, 10 years ago, it took 6 months to get pixels up on the screen, right? Now it takes 6 minutes. So from a creative medium point of view, this stuff is all new. And it's so early that we haven't figured out what's effective and, you know, so much to innovate upon. Or certainly, you know, there is a lot there, but there's a lot remain to be done as well. What are those most compelling applications to go beyond the first, you know, for me, the 360 is pretty cool, but after 45 seconds, I'm ready to go on to the next, you know, the next viewing or whatever, because we haven't gotten good from a storytelling perspective. We've just, you know, gotten good at, starting to get good at the technical side. And so we need to start getting good at selling the story and the emotion instead of just selling the technology.
Yeah, right now we're, as a industry and also, you know, as a field, we're in the sort of breadth first search mode where, you know, we're coming at it from different angles, high end, low end, and so on and so forth. So it's unclear what's going to stick and what isn't. You know, what I kind of have been thinking about is, I think about YouTube and how popular YouTube is. And I think once we can get the ability to create these experiences to be as simple as making a video on YouTube, then we'll start to see it take off. And you'll have, you know, basically people creating content like they create YouTube videos, you know, for good or for bad. And the other thing that you'll find is that as the technology improves and we get better streaming, like live streaming video and live streaming 360 video, you know, you could be, you know, you could have your head-mounted display on, and someone happens to be in Hawaii right now with a 360 camera, and they're hooked up to some app, and now you're in Hawaii too, and you can talk to them and say, why don't you go walk down to the beach? The guy walks down to the beach, you know, and so on and so forth. So there's going to be a lot of different avenues for where this could potentially take off. I don't know which one is going to be most successful, but if I had to make a guess, I'd say from a sort of mass scale, it's going to be the consumer-generated content and people viewing it as akin to the YouTube model. I think that has the potential to be the biggest, you know, thing in VR. I mean, we're still going to have, you know, cool games and innovation in that space. We're still going to have, eventually, and they're starting to do this, you're going to have movie theaters where you go and you sit and you put on your head-mounted display. All right, so you're going to have these VR cinemas, you know, and they're already doing this in China, which would be really interesting, you know, and instead of Blu-rays, there's going to be VR-rays, okay, that'll come out, you know, different encoding scheme or something. So I think it's all going to happen. It's just, you know, which ones are going to be popular and which one isn't is tough to say. But if I had to make a guess, I think once you can get to the level where you can create content at the same level and simplicity of making a video and putting it onto YouTube, then we're going to see it really take off.
So the user-generated content, right? The UGC. Dr. Marks, any thoughts about? I guess what really the question is, like, people could say that VR is the highest level of research in HCI, right? Human-computer interaction. And I guess from your perspective, what have you found that humans? And really, what it does is it allows us to, you know, quantize what humans like and dislike and pay attention to. What have you found that humans are good at creating and good at enjoying? Dr. Marks, if you can.
Well, I think it's, I think of it in this really simple term as kind of this cost-benefit trade-off. The cost is either money or encumbrance of wearing stuff versus the benefit you get out of doing it. And right now, I think a lot of people see 360 videos not giving them enough benefit for the cost. Even if the content is free, there's the encumbrance factor. So until that changes, it's not going to fix itself. So if you have a really great story, you can fix it that way. Other ways is have a really interactive, high-end experience. That might cost more too, though. So you just have to get that balance right. Otherwise, nobody's going to be excited about it. And for me, and from the world of gaming, interactivity is a kind of requirement for it to be a high value. So 360 video doesn't give the interactivity, so that's not really the area our company is pursuing so much.
Not yet.
Well,
we're working on that.
And then there's also the production costs of some of that, which is non-trivial. And especially if you become into light fields and things, then the production costs shoot way up. So then the cost is too high for the benefit, unless it's just so mind-blowing that its benefit is so high. So I think right now the sweet spot that we're seeing right now is the same level as what we already were doing with games, but put into VR. So you can do a lot of the things just in a more immersive way than you could do them before, and the cost isn't really any higher than making a game. The cost, only extra cost, is the cost of the hardware to the consumer, unfortunately.
And that cost, I think, I mean, that obviously we'd love to see that come down, but people pay $800 for a cell phone, right? And so I think part of it is we're not offering enough value beyond that coolness factor and the wow factor. But, you know, when we start getting real useful apps or really, you know, super engaging games, then that obviously, you know, what value are you getting out of it? So not just bring the cost down, but bring the value up. And also something to add, going beyond 360, I think a big breakthrough, hopefully soon in the near future, and people are already doing it, it's just a matter of going mainstream, is once we have the hand controllers are such a perfect fit for VR. Right? I know, you know, Richard, the PlayStation Move was, they sold a lot of those, right? But suddenly for VR, it's even a better fit. Or the Sixth Sense Razor Hydra, right? Like, was a flop. And then the month that the Oculus DK1 shipped, they sold more in that 1 month than they had in the entire, you know, history of the thing, right? Because it was such a good fit. And so when we get those hand controllers and quality hand tracking, for not, you know, gyro-based hand tracking or, you know, limited field of view tracking that Richard talked about. If, you know, how can I reach down here? You know, you don't want to have to always interact where you're looking. That's a problem. But when we get really high quality hand tracking, and, you know, people are offering that, just not mainstream yet. Once we get that for mobile, and, you know, it's at a low price point, $100 or whatever, and that works well, then we can start having those well, not the HTC from a graphics rendering point of view, but from the HTC from the PlayStation VR sort of level of experience on mobile. I think that's going to change everything.
Beautiful.
Because those interactions will be similar. The graphics, of course, will be better, but the interactions, I think that's what makes just VR. So for me, that's what makes it so engaging.
That's why you had this course, right?
Yes.
Outstanding. Yeah, this talk was, you know, very, very much look forward to by all the attendees, and essentially it serves almost as the closing remarks for the conference. So I guess any you know, de facto closing remarks, because this is for most of us, this will be our you know, closing ceremonies for SIGGRAPH 2017. Any kind of anything you'd like to say about the research of this year? You know, the giraffe, perhaps. For anything that is stood out to you this year and that you look forward to seeing next year.
I suspect we all could say yes, and we can't talk about it in some cases. But yeah, I mean, just so much is coming out every week, right? Like every day, it's hard to keep up with some, you know, fascinating. I mean, you go look at all the new headsets out there. It's crazy how fast things are happening. And so, yeah, I get excited every day. I read about a new piece of hardware, or try a new demo, or a new application, you know, that's doing something innovative that I haven't seen before.
Oh, please.
Thank you for your talk, and I wonder about the future of VR interaction. So how do you think about using brain waves as a controller, or sensing emotion? Yeah, such as.
So I've had some experience with brain-computer interaction. I had not really been able to get it to do what I wanted it to do. I couldn't move objects with my head, you know, with my mind. I know some people have been successful. It really depends on how invasive you want to be. But I do think that is an area that still will be is going to be explored. Now, being able to detect emotional state, that can be done. And that, I think, is very interesting, especially from a gaming perspective. If I can detect your emotional state when you're playing a game in a VR environment and tailor the game based on that, I think that's going to make that game so much more compelling. I don't know if Rick can say anything about that or not. But
I think I agree that emotional state detection is an interesting thing. The brain interface, I don't know that it's necessary in a lot of cases we have great ways to manipulate objects and select objects and do that already. So the goal of the brain interface sometimes is to create this magical effect that you can't do. You're not using any of the ways we already know how to do it. And in that case, it's just got such a high bar to reach to be as good as the things we already can do. So you can definitely do a small amount with the brain interface, but I don't think you should try to compete against the things that we're already good at with brain interfaces. Brain interfaces should be used in ways that for things we're not good at and already. So that's my opinion with those interfaces, that maybe we're trying to solve the wrong problem sometimes with them. And what you do is you get a very low fidelity version of a mouse or something, then that's not a better mouse. It's kind of a neat mouse, but it's just not better. Eye tracking, I think, for example, does a lot of what brain interfaces are trying to do much, much better. And eye tracking does it better than we currently can do it with hand trackers. So that one I like. And it feels a little bit like what brain interfaces are going for. But maybe on the emotional side, some of those kind of sensing, the camera-based techniques for that are also impressive. And I think that again, if you put them up against the same problem, I'm not sure that the brain interfaces will win.
Sorry.
I was going to say I agree completely, and I think it gets back to that multimodal input, right? If you're using whether it's the emotion, adding on to these things instead of trying to replace things. So, if you have a different emotion, then, it might affect what you're doing with the interface in some way, right? If you're angry, maybe you'll get a faster response or move ahead in the queue or whatever. But also, I think for like relaxation applications, obviously, that biofeedback, like, that to me seems like sort of an ideal case. But to echo what Richard said, it's the data, my understanding, is so noisy and so subtle, it's difficult to have sort of precise control. So let's add on to something to enhance something instead of replace it, I think.
It's actually the exact same answer as with gesture recognition. If your goal is a button press, a gesture is a bad choice. Buttons are way better at button presses than gestures are. Same thing with brain interface. If that's the goal, is just a single button press, then for that, it's just probably not the best choice.
And even eye tracking, like you mentioned, I think that's perfect for multimodal input. Forget if it was you or Joe or Richard about, looking at, I think that was you, Joe, of looking at something and then the system knows it's looking at it so you can, toss something out in the world or whatever it might be. So I think that's a really good example of that multimodal sort of input. Eye tracking, in my opinion on eye tracking, is by itself, I don't think it's a very good interaction technique, but if you mix it with other things, it suddenly can become very compelling. And so BCI might be something similar, right? Let's enhance something instead of trying to replace it.
Thank you. I partially agree with your opinions, but I agree with the to control button or moving something is if I want to control something, button or gesture would be better. But especially people don't know about their own emotion or their memory or such as the vague information. If the brain waves can detect those informations better than human, I think there is a possibility to use those informations as to design the VR space or until now, the interface or interaction was one and one. There was one input and one output, but recommend such 2 or 3 vague outputs. So I think those uncertain information can also have possibility to using as an interaction in VR. So how do you think about those points?
I think we're in agreement, actually. I think we're saying it can be used to enhance, but maybe not replace is a lot tougher problem, I think. So at least the way I'm understanding you, I think we're in total agreement.
Yeah, I think every interface modality adds context. That's what they all do. And sometimes they add context in a way that helps each other. And pointing adds context. Having a thought that's in a certain space, if that added context to my choice, that would be a great input.
It's akin to wanting to have visual, auditory, haptic, all these output modalities. Input modality, we'd like to have as many so that we can then use them, fuse them together, run deep learning on them, because deep learning is the thing now, and then come up with something, really cool, right? So.
Okay, thank you.
Hi. So following up on question about detecting emotional states, what are the other effective methods that you think exist today?
I didn't hear that. Did you get that? I didn't hear the last part.
The emotional state, what other methods exist to detect that?
Galvanic skin response. You can measure heart rate, you can measure temperature of the body. You can measure, there's a whole field called affective computing. And the whole mission of affective computing is to measure people's physiological and emotional states. And they use all different types of sensors to do this. And then once they get that information, then they can do various things with it. Some people use it in adaptive tutoring, some people use it for relaxation. Some people have even used it for games. So there's a lot of different hardware. Her name is Rosalind Picard. She's at MIT, and she's like one of the top people in affective computing. If you were to look her up, you'd see all the types of things that they do and how it could be applied to a lot of different domains.
Thanks. I feel like all of those sensors would take away from the feeling of the presence in the VR, because there's all these things attached to you. Are there any devices that are not as invasive or as heavy on the body?
Actually, yes. In fact, on the show floor, there are computer vision-based algorithms that can do things like detect heart rate,
right,
and temperature of the body. So that's a device that you wouldn't be wearing, and you just have a camera sticking out there, and it would be able to detect those things. So there are unobtrusive methods for detecting those types of responses.
Thank you.
I think we have to go.
Okay, well, thank you for attending. And I think Joe and I will be outside, Richard as well, so we can continue the discussion for a few minutes if you'd like. Thanks for coming.
Thank you.
Come try a demo. Oh, sorry. Well, there's 10 people.